to convince you too much on zero knowledge, but a lot of the work we've been doing currently has been on hash-based narcs. And I'm going to just give you like the very high-level overview or why we care about hash-based narcs and why they are like quite nice. So what do I mean by hash-based narcs? I mean snarks which are secure in the pure random oracle model. So I'm not going to allow myself any cryptography, no elliptic curve, no lattices, no algebraic assumption. I just want to use a random oracle. If you construct a snark in this model, you get like a lot of benefits. One of them is the fact that you can get like a transparent setup. That means that when I need to do the setup for like the snark, the only thing I need to choose is choose a hash. And if I have a problem with that particular hash, I can just choose it without having to go through any expensive procedure. Further, since this is just like random oracle, there's no lattices, no elliptic curve, there's nothing, I don't have to do any public key operations. So my prover can be fully implemented in, with the public key operation, so with the private key operation. So the prover can be extremely efficient. To give you like just some concrete numbers, this is something I run on my laptop like, I think I did it like a couple of months ago, so it is possible that these numbers are updated. But if you want to commit to do the 26 elements with an hash-based scheme, you can do this in around 300 milliseconds. While if you're using an equivalent group-based commitment scheme, this will be on the order of 3 minutes on my laptop. So there's like a very important efficient difference between prover in hash-based schemes and other ones. So every benchmark is a lie, so this is also a lie, but this gives some intuition on why like hash-based proof systems have like very efficient provers. Further, we have extremely well understood security for like arguments in the random oracle model. We have bounds which are tight, and we can set parameters very efficiently. Finally, yesterday we had like a lot of talk about quantum, about the fact that this quantum daemon becoming very close, and hash-based narcs can be shown to be secure in the quantum random oracle model, which means that we can say that they are post-quantum secure. And all of these features have made the hash-based narcs to be like widely deployed in a bunch of applications, such for example, the biggest one currently by number of users is in Google Wallet. So I want to just give you a feel about what kind of parameters we can get for like state-of-the-art hash-based schemes. You can get like prover time, which are in the order of a small hundreds of milliseconds to like a few number of seconds. Proof size ranges between 100 kilobytes and 400 kilobytes, and verification time can be from 100 microseconds to a couple of milliseconds. This in particular, the last one, we do not know how to achieve currently with any other assumption that is not hash-based. And there's been like, because of this, there's been like a flurry, like this, all these numbers come from like a flurry of works on like efficient hash-based proof systems. I've selected a few of them. I hope I've not slighted anyone about them. But if you look at these works, like there's one thing that jumps out, and it is that most of the progress in hash-based narcs in the past like 5 years has focused on getting proofs which are succinct. And zero knowledge is something that we actually need for a lot of application, and we know how to achieve it for hash-based narcs, but the generic way that we know how to achieve it with are usually kind of expensive. So in this work, we ask the question of, can we actually get zero-knowledge variants of these state-of-the-art hash-based narcs, where the overhead is like a low-order term on both the prover, the verifier, and the argument size. So I'm going to just jump into it and give you the results. So I'm going to assume that a few people here have been to IOP Fest. I'm going to still motivate the things, but we see that like hash-based narcs, they're based on like the interactive oracle proofs, and in particular, they're based on something called interactive oracle proof of proximity. And as our main result, we're going to present one of these interactive oracle proof of proximity for one class of code, which are constrained codes. So intuitively, constrained codes are codes which admit, I'm going to introduce them properly later on, but which admit like a particularly simple folding operation. So here I'm going to give you the main results. So I'm going to try to get like an IOPP, which is going to be for interleave Reed-Solomon encoding. So n in this case is the number of coefficients I'm encoding. I'm encoding it in a domain of size m, and the interleaving factor I'm going to think as like a logarithmic, like a log n interleaving factor. And I want to achieve 2 to the minus lambda security. In the notion I really want is rumba around security, but let's just say security for now. So, and I'm going to denote in red the overhead of like this proof system compared to the non-ZK variant, which in this case it would be like instantiation of where. So the proof length, which is a measure of like the prover time, is the proof length of where plus like a little of lambda with tilde because we might have like some polylog factors in there of field elements. You actually get the same exact query complexity as the word protocol. This is what translates later on into argument size for the compile argument. And both prover time and verifier time are essentially the prover time and verifier time of the non-ZK variant plus a little of lambda, plus like some polylog factors in lambda. All of this while still achieving perfect honest verifier zero knowledge. So when in reality, this is just one instantiation of a framework that we built. If you've been to Ale's talk yesterday and to Pratyush's talk yesterday, you see that like a lot of like the state-of-the-art IOPPs are built from like a general framework of reduction of interleave codes. We actually do the same work, but we formalize this framework and we do it all in zero knowledge. And you get like, if you instantiate it, you get like zero knowledge over version of like existing protocols with zero overhead, including things like, for example, breakdown, were some version of Ligero, and others. And you might say like, look, Giacomo, why are we caring about honest verifier zero knowledge? It is because in the that's a black bar. If you have honest verifier zero knowledge in the IOP, once you compile it and you make the argument non-interactive, you get like malicious zero knowledge in the argument, or actually just zero knowledge in the argument. So further, like when we do this, our version of like breakdown achieve like some improved guarantees. So for example, we go back and we do like list decoding, and we achieve straight line knowledge soundness for all of this protocol. This is important for like things like for post-quantum security and UC security. Further, this is a generic framework which you can instantiate with any linear code that you want, as long as the linear code has a zero knowledge property. I'm going to talk about this later on as well. And finally, we also developed a framework for composing zero knowledge interactive work reductions. If you've seen William talks, interactive work reductions are a way to abstract like some of the common patterns in constructing the IOPs, and we show how to construct zero knowledge IORs. We show a toolkit for them and how to compose them while preserving the zero knowledge property. Okay, so look, this is somewhat of a practical conference, so you might ask us, okay, look, asymptotics lie, so what about concrete efficiency? And I'm gonna like do something a bit different, which I haven't seen in a lot of talks, and make the claim that we need to have better ways of comparing protocols, because modern protocols have a lot of parameters. And typically, there's like a very important trade-off between the prover time and the verifier time. If you want to think about Fry, for example, this is calculated by the rate of the code that you're using. So comparing protocols are not just 2 points in the graph. We really have to figure out what this trade-off is and what the protocols end up like achieving. And so what I'm going to do a Pareto frontier. So I'm going to plot this trade-off between two things which I can compute without having to implement things, because I'm really bad at implementing things. So I'm going to look at proof size, which correlates directly with prover time, and argument size, which is a good proxy of verifier time. So yeah, the proof size is directly proportional to the number of hashes the prover does, so it's a good proxy of prover time, while the argument size is the number of hashes that the verifier does effectively, and so it's a good proxy of verifier time. So if you haven't seen a Pareto frontier, this is what it looks like. So basically, there's going to be like this line. These are like the optimal points which achieve the best trade-off. So these are like the designs which achieve the optimal trade-off between prover time and verifier. Anything in the internal region we won't care about because it will be dominated by things on the frontier. So, okay. Here's what it looks like. So the black line is a where, while the blue line is a ZUK. So I've helpfully zoomed in a little bit into this. So you can think of the area between the two curves is the overhead of adding ZK. So, it's not zero, asymptotically it is zero, but it is, I think, really acceptable. So for example, like if I look at this, there, the overhead is around 5-10 kilobytes for these sizes. These are for an argument of 2 to the 26 field elements. So, and once you go, like, once the argument size gets larger, this really goes to zero asymptotically. And this actually holds, like, for a lot of argument sizes. So here I plotted the Pareto frontier for many different argument sizes, and you can see that the overhead is almost a constant over like over the non-ZK version. Okay, so I think concretely this shows quite well. I also like these plots. They're a bit weird colored, but yeah, this shows how concretely we actually get like a very small overhead. So how do we do this? Now I'm going to tell you a bit like about the techniques to go into like achieving this. This is a bit of a weird talk because there was one at ZK Summit in which I covered some of the similar thing, but I'm going to tell you the roadmap, and then I'm going to focus on one component in constructing these zero-knowledge IOPs. So if you've seen Ale's talk yesterday, you can see, this is an instantiation of the same framework, but we're going to work in like a zero-knowledge like version of it. So we're going to have like two instantiations. One of them is the sublinear protocol, which is you can think it of as a zero-knowledge version of the breakdown protocol, if you may it. And this is going to be built by composing a few different reductions. So first, there's going to be a reduction which just takes whatever relation you want, say R1CS, and turns it into zero-knowledge problems about constrained code, constrained interleave codes. We're not going to see this at all. And then we're going to have a zero-knowledge sum check. And the way you should think about the zero-knowledge sum check is that it will reduce a claim on n coefficients to a claim on n over k coefficients, while making like O of lambda queries over an alphabet f to the k. So here there's a trade-off between like how much you reduce the problem and how much the argument size goes up. And for the sublinear protocol, you should think of k to be around square root of n. Then there's going to be like a trivial ZK protocol, which has linear communication and verifier time, and we'll also have like non-zero overhead. But it's always fine to apply once the problem size has been reduced enough. Then we're going to build on these ideas, and we're going to do a subsyn protocol, which is a zero-knowledge version of WER. So it's going to look almost exactly the same. So I'm going to still, again, apply like a ZK sum check, but now I'm going to set k to be logarithmic, so I'm going to reduce by a log factor. Then after you've done this reduction, you go from an interleave code to a base code. So I don't have the ability to fold again. So what I'm going to do a zero-knowledge code switch, which I'm going to switch from a code to an interleave code so that I'm able to actually fold again. And then I'm going to fold again with the ZK sum check, and I'm going to repeat this process roughly log n over log n times. And finally, at the very end, I'm going to apply this trivial protocol again. So in the last talk at ZK Summit, we should be online by now. We did the ZK sum check at ZK trivial. Today, I just want to talk about ZK codes and the ZK code switch together with the relation that makes these things work. Okay, so this is my plan. I think I will not be able to do all of it, but we'll see how far we go. So let me just do a little reminder of what error correcting codes are. We've seen a lot of these things before. This is just I'm taking a message and I'm adding some redundancy to it. In this talk, we're going to be focusing about linear codes only. And so I'm going to always denote by GC the generator matrix of the code. The map needs to be injective. The annoying part about error correcting codes is that they don't really, by default, give you some privacy notions. So if I am an encoding of a witness, which will happen in like these proof systems, and the verifier is going to query this encoding at some points, this can leak information about the witness. And in fact, In many cases, it will. This is a completely deterministic map. It's injecting. It will leak some information about the witness. And an example of where this is like problematic is like when you have a code with a systematic encoding, because they're like, look, the first half of the message is already like is just already the witness. So if I touch it, I will learn things. And this is just some notation that we're going to be used for later on. I just have it here on the slide for completeness. Okay, so we want to solve this privacy problem. We have this annoyance that like error correcting codes as they are, they don't give you privacy. How do you go and solve this? Well, there's a very beautifully and widely studied notion of zero-knowledge codes. Oh, sorry. So what are we going to do? For zero-knowledge codes, you want to solve the two competing constraints. So you want the code to still create distance. You want to create redundancy in the message. But you also want the reading code word should not reveal anything about the message, which are two contracted constraints. Okay, let's I don't know how to do this, so I'm going to look at the only thing that I know how to do, which is polynomials, and I'm going to think about with Solomon codes. So just to remind you what they are, these I take a message, I interpret it as a polynomial, and I evaluate it over some subset of the field. So okay, here I've like I put 3 points in the field, and I'm showing you that with 3 points there's like a lot of like oh, what happened? Okay. There's like for 3 points there are like a lot of quartics that pass by it. So so for any like choices of point that you reveal, there's like many polynomials that agree with this. This is just interpolation. Like as long as the degree of the polynomial is larger than the number of points that are revealing, I can complete the curve in many different ways. Okay, we're going to use this to build like a zero-knowledge code. Which would appear in the slide eventually. Okay. So the way that I'm going to make a zero-knowledge code, a Solomon code zero-knowledge, is that I'm just going to like take the normal encoding and I'm going to add some randomness R. And this R will give me enough degrees of uncertainty so that like whenever I read a few locations of the code words, I don't learn anything about what the F was. And you can define like a zero-knowledge encoding property. And in this case, the encoding will take like some message and some randomness. And we want the encoding to be that any like small amount of locations in the encoding are efficiently simulatable. Good. So this is the notion of a zero-knowledge code. Now we're gonna, and I'm also gonna use this notation that since like the encoding is a linear map, I can split the encoding matrix of the randomized encoding map into like one part which depends on the message and one part which depends on the randomness. This is going to be useful for the code switch later on. Okay, good. So zero-knowledge code, this is all prior work. Now I'm going to show you how to use the zero-knowledge codes to do a code switch. And before that, because this is somewhat new, I'm going to do a code switch again. So I'm going to start with like some linear claim about some code word F of some sort, so V and U. And I want to like change it to a claim about another code C2. It's like a version of the generic code switch that Ale presented like at IOP Fest yesterday. And the protocol is going to be exceedingly simple. So first, I'm going to ask the prover to send me an encoding of the same message F that was underlying the code word F under the different code C2. Then I'm going to do an auto-domain sample. So an auto-domain sample is something that we're going to be using for list decoding. And in a certain sense, it's going to pin down the prover to a single message underlying the code word is committed. I'm going to do a generic one where you just use a zero evader. This is not too important for now. You could think of this like just being like a univariate evaluation. And here's the definition of a zero evader. Okay. Now I sent a code word. The prover, in a sense, committed to a unique message underlying the message it is sent. Now I want to make sure that there is consistency between the new message and the old message. So what I'm going to do, well, I'm going to do the only trick that I know, which is to spot check things. So I'm going to spot check things. So, and to do that, I'm going to query the original message as a few position. And what I'm going to do, I'm going to set constraints on what the new claim should satisfy. So we're going to have like an automate constraints. We're going to have the original constraints, and then we're going to have this constraint, which basically means that when I take the message encoded by G and I apply the ZIF row or the generator matrix, I get exactly what I read from the oracle. These are some problems. One of them, which doesn't have it, that this protocol is quite nice, is knowledge sound. So you get like some zero knowledge soundness, and you can actually play a lot around with what the distance parameters are in these errors. One problem that it has, it doesn't have zero knowledge, because this auto-domain sample leaks information about the message I'm encoding. This is not great. But this problem as a protocol has like an even worse problem in that it is actually not complete. Since we're gonna need like our witnesses to be encoded with zero knowledge codes, the encoding map is deterministic. Is non-deterministic. So what I'm reading over when I'm reading from the original message will be randomized. So it needs to depend on the randomness of the previous encoding. And here we currently have no way of doing it. So no way of keeping track of it. So we need to have a solution in order to actually carry the randomness of the previous code into the code switch. OK, let me give an attempt at this. So I'm going to be again in the same thing. Now I'm going to make it explicit that I'm using like a zero knowledge code for this encoding. And I'm going to do things in a very similar way. But now I want to use some randomness in order to make sure that I'm not leaking and that I can carry forward the randomness of the previous encoding. So I'm going to use 3 pieces of randomness, which have like confusingly similar names. Now, I'm going to do almost exactly as before. So the start of the protocol will be that I encode the old witness under a new fresh ZK code, which is C2. Now I need to do 2 things. I need to randomize my auto-domain sample, and I need to carry the randomness from the previous iteration forward in the code switch. So what I'm going to do, I'm going to use a second ZK code, ZK in this case, which will encode R, which is the old randomness, some new randomness M, which I'm going to use to hide the auto-domain sample, and then R double prime is going to be the randomness which hides this message. And I'm going to just send these 2 oracles now here. Of course, you can batch these things appropriately. Now I'm going to continue as before, so I'm going to actually just do a zero evader. But now when the prover does the auto-domain sample will actually be on the message encoded by the first code, and then the message encoded by the second code. So I'm going to do a joint auto-domain sample on both messages at once. Then I'm going to still do my spot checks as before, because I can read all of these and I'll be happy. And now when I'm going to just write down all the linear constraints which are induced on these joint systems of things. And now this new claim is going to be a claim on like both G and S, so like on both of these code words. So I'm going to continue with this, and I'm split things according to the matrix decomposition. Now, this might be a bit confusing, but you can, if you do the derivation, it's kind of like clear how these constraints came out. I'm just like rewriting f at zi using the encoding map of the zero knowledge code. Now, M can mask the auto-domain sample. In reality, you need some version of privacy from the zero evader because you want, for example, the contribution from M not to be zeroed out by the zero evader. So there's a version of private zero evaders that we define in the work. Now, the soundness error of this, well, it's a bit worse. Now you have like this, product of the list sizes, but it's not too bad because the zero evader error we can amplify as we want. So this is code switches sound. Good. How much am I doing on time? You have 3 minutes. 3 minutes. OK, good. Good. So this is going to be the old code switch. Like with this, like we can see, we have basically done the entire protocol between the ZK Summit talk and this talk. So I'm going to just show you like Yeah, we're going to ignore that. So I'm just going to tell you the relation that we care about in this work is this joint constraint relation, because as we saw before from the code switch, we don't have now the luxury of only having constraints which are on a single code word, but we want to think about joint constraint about messages encoded by different code words. So here's what the relation looks like, and I'm going to just walk through it quickly. So you're going to have a constraint, which in this talk, I'm just making an explicit vector v. And you can make a scene description out of it, of course. You have a variable constraint mu. You're going to have code word f and s. And your witness is going to be the messages and randomness used to encoding the entire f and s. So in your, oh, this is not a pointer. Or is it a pointer? It is not a pointer. So the relation is about like f and s, which are honest ZK encoding, such that the joint message by f and s satisfies some linear constraint. So this is what we deal with throughout our reductions. So exactly. So and we call this a joint constraint. So okay, now I'm going to just give it back. This is my last slide. So Elon is happy, reasonably happy, and I'm going to just tell you how we put everything together. We get the succinct protocol. Okay, so I'm going to start, and I'm going to start with a interleave code with an interleaving factor to do decay. So we haven't seen it in this talk, but I'm going to do the zero-knowledge sum-check protocol, which you should think about it as a sum-check protocol a la Libra, where I'm using like some masking to mask each of the sum-check polynomial. So this is the masking that's done. And I'm going to apply like k rounds of sum-check. Each of them will reduce the problem size by a factor of 2. So overall, I'm going to reduce by a factor of 2 to the k. At the end of this sum-check, I'm going to define a virtual oracle, which is the fold of the original oracle on this part. So this reduces by a log n factor with 0 overhead by prior work, which I'm not mentioning, by prior like talks. Then I'm going to apply the code switch. So I have this fold. This fold is encoded under the code C. And now I wanna code switch to a new interleave code so that I can fold again. So I'm gonna send the re-encoding of the fold under F1 plus the masking that we saw before in the code switch. I'm gonna do the auto-domain sample. And then I'm gonna query the fold. This is gonna be reading all of lambda queries, each of them of an alphabet of size 2 to the k. And I'm going to switch in ZK to the interleave code. Then I'm going to apply the ZK sum check, and I'm going to reduce and repeat this for a bunch of times. And finally, I'm going to send like the final oracles for this trivial protocol, where essentially I just mask whatever at the end. And this is fine because you're going to pay some overhead there, but the size of the instance at this time is kind of like O of lambda, is tiny. And if I look at the complexity, roughly, again, the red is the overhead. So the query complexity overhead is just the query that you have to do to these new ZK code masks, which with a setting of parameter, this is like little of lambda, so it is negligible. And the proof length is just basically added by how large the ZK codes are. And again, with setting parameters, probably this is like little of 1, less overhead. Good, so yeah, this is all of it. And I'm sorry I had to piece it from different talks, but I think, yeah. This is overall the entire protocol.
A quick question.
Thanks. RS code, of course, is a zero-knowledge code, but I'm wondering if the breakdown-like code or Spellman-like code are also zero-knowledge code?
Okay, yeah, so that's a good question. So the breakdown code, if I remember correctly, is systematic, so it cannot be zero-knowledge. And we know some linear time encodable zero-knowledge codes, such as, for example, those in BCL. Unfortunately, I think that there aren't that many of them, and I think a very interesting open question is figuring out which other linear time encodable codes are zero-knowledge.
Okay, thanks.
Okay, let's thank Giacomo again.
Thank you.
improve the resolution? Like the resolution wasn't so good. You see how like it's not. It's not like
Che la
crisp
risoluzione
clear.
un po' basta.
No. Okay. Where's the next speaker?
In parte immagine. Allora, tiralo fuori dalla tasca, dai.
Lo stacco?
Sì, sì, aspetta.
Prima che te lo posi poi un problema.
Ok.
Grazie mille.
Okay. The next speaker? Ah, here. I didn't see. Okay. Yeah, yeah.
You need this one? You prefer this one or that one?
I can do this. It's
That
we are
one?
already a bit late. So.
Sure.
Yeah, yeah.
Okay.
Okay, so we're gonna have now Andrea. He's gonna talk to us about Usain Bolt.
Yeah, hopefully. Let me just see. Yeah, hi. Andrea here from Bain Capital Crypto, and I'm gonna present a new PCS called Bolt. This is a joint work with colleague Ron, who is down there, and Kobe, who is hopefully watching us online. So Bolt is a new multilinear PCS that we built from something we called sketch code. So I think audience here is fairly familiar with what are PCS and what is a multilinear PCS, but the idea is that we have this evaluation tables as a functions on Boolean hypercube, and we want to have something similar to what we have in all PCSs, which is prover can somehow commit to the table F, later get the query point, call it Z from the verifier, and prove the evaluation of that polynomial in Z. And of course, we want verifier to be succinct, which means that it will run in time way less than the size of the table and also memory. So we will go through how this construction works. You can have it in many different flavors, as we love to say. So you will have, for example, pure theory flavor if you care about big O notation and not that much about constants. If you want to deploy it, you might really care about the constants. So then you can optimize for prover speed or for a proof size, depending on which setting are we. Is this like a client side, server side? Can we recurse? Which hash are we using? And many other classical stuff. So I will not spend too much time on this fully asymptotic version, but the idea is that so far the state of the art, we can say, was in around 8n additions to encode something, which we have with RAA codes used in Blaze. And we can now do stuff with 3 plus some epsilon amount of additions in the theory. And also the codes are of very high rate, so there will be also not that much hashing. The proofs are going to be log n square, but with a very high constants. So theory Bolt is probably not something that you will ever use in practice. Okay, so before we go in how it works, this is just like a quick table to show what we were able to achieve. We wanted to show stuff for this like very high polynomials as 2 to the 30, which we emphasize here. And we compare ourselves with Ligerito. We are this like Reed-Solomon-based scheme. We have Blaze, Breakdown, and then Bolt. Breakdown also comes with a different distance trade-off. So this is all on like M4 Max. So it's like a very, so to say, cheap hardware. You don't need a GPU cluster and who knows what to run this. And essentially, you can commit to these instances over 32-bit field in roughly 1.2 seconds, which we think is amazing. The proof sizes we put for now just in like unique decoding domain. I think you were all here for a talk about least decoding and proximity gaps and stuff. We will get into that later, but the idea here was just to show like a pure unique decoding regime for now. And yes, like there is this trade-off between proof size and prover speed. So just by paying a little bit more on the prover side, we can substantially reduce the proof sizes. Okay, so the main goal of this work was to achieve something that is very hard. So there's been a lot of work in hash-based PCS, and seems that that's going to be a new standard. Speed, quantum stuff, whatever. So we have kind of two different versions of schemes. So we have a lot of work being done in Reed-Solomon codes, and you're fairly familiar with Fry, Weir, Steer, etc. So in big O notation, everything with Reed-Solomon will run in n log n. And then we have also like linear time encodable codes, such as Breakdown and Blaze, etc. But what none of these linearly time encodable schemes seem to took off, and it kind of always come with a very large, larger proofs, which makes them very impractical for the deploying in systems. So our goal was, okay, can we make something? Oh, okay, sorry. Can we make something that is faster than Reed-Solomon, but not have a massive proofs, and still have something reasonable to encode and deploy practically? And yes, this was not an easy task. There is a lot of things you have to think about. It's, okay, first like encoding time, then proof sizes, and also this IOPs. So Giacomo and a lot of other people yesterday were mentioning this technique code switch. So it's kind of standard how you do stuff today, but it's very easy to have a very complex IOP for code switch, which actually, when you start deploying it practically, is not that nice as it's on paper. Okay, so first, what we use are these LDPC matrices, or people are familiar with as low-density parity checks. And you're probably familiar with low-density parity check codes, which are like these codes with parity check matrices are very sparse. So we use them here in a very fun way to actually encode stuff. They have a very important property that if we look into the kernel of these matrices, there are no non-zero low-weight messages. So that's going to be a very important thing for arguing distance of this code. Another important thing is that this matrix is sparse, so we can encode with it. We can multiply vectors with this matrix in a linear time. And there's a lot of work on efficient IOPs for checking sparse matrix vector multiplications. You might be aware of Spartan, for example. This is also this new work called MulPerm, which gives a very efficient way to do these things. And also the encoding matrices we use for code switch have to have some properties, which are that their rows of these matrices are efficiently, can be efficiently extended and evaluated. And so far, there are not many codes that have these properties, and LDPCs have this property naturally. Okay, so then we also use what everybody was mentioning is this code switch. I'm not going to go there too much, but the idea is you can start with some code, and in all these PCSs, we have this interleaving. So you want to encode as much data as possible with some fast code, and then reduce claim to some other code which has some better properties. Might not be that fast, but since anyway instance is folded and substantially smaller, we can pay for like larger encoding time in this switch. So again, I love to look into these pure Reed-Solomon schemes as also code switching just from Reed-Solomon to Reed-Solomon, but it can get more complicated and with more ingredients. So also the big idea of this work was, can we have also as simple as possible code switch, IOP, because that will also impact a lot practicality of the scheme. Okay, so let's just briefly look what is this thing we call sketch codes. So we first start with this sparse matrix and some factor alpha, which we always take to be less than 1. So you can imagine that this matrix will compress your message into something smaller. Okay, so first you apply this sparse matrix. We can, as I said, multiply with this matrix quite quickly. And then we are left with something that is smaller than the message. So you can imagine that rate of this code is high, larger than 1/2, and you want to get as close to 1. So then you're left with something smaller, and then you can have another code, whatever code you like, and encode this already encoded syndrome, which we call sketch, with this different code. The code itself is systematic, so you can see that you just append the message, you do one sparse matrix multiplication, and then you encode that with another code. And it turns out that this has a very nice encoding time and also very nice distance. So encoding time is very easy to see. It really depends on sparsity of this matrix H, or so to say, number of non-zero elements you have there, and whatever is the encoding time of the another code you want to use. Distance is also not that hard to argue. So as we said, in the kernel of H, there are no low-weight messages that have zero encoding. So if you start with something that is higher weight, you're kind of done. If you have something that is very low weight, then this other code C will add distance to it, and you will end up with a pretty neat distance. Similar time when we published, there was also another work that's called the sketched code, concurrent with us, and they used it to improve encoding times of breakdown. Okay, so I know a lot of people love to encode rows in interleaving. We kind of work with columns. It's just more natural to me. So at this point, I think everybody here is aware of the Ligero techniques, where you start with some matrix, you encode its columns or rows, verify sense random linear combination, and we fold it into something else. So we do that here also. And as I mentioned, we wanted to have the most simple IOP ever. So as I will show you in the concrete instantiation, we are also going to rely on Reed-Solomon codes. So by looking into IOP of this code switch, it's almost same as IOP you will have in Weir or Ligerito. So it's going to be very efficient to just re-encode much smaller message once more with Reed-Solomon. And you also have to do this, this thing to prove that you correctly multiplied with this sparse matrix. Nice thing about this is, as I said, we already have a lot of work that optimizes this. And in further cases where you might care about zero knowledge, or when you're committing to a lot of polynomials at the same time, this second claim can be amortized and batched across all instances. So in practical deployments, you can amortize this across all commitments and have something very efficient, or either outsourced to some server. It will not affect zero knowledge or other properties you need. You can also do it client-side. With this new work mulperm, it's just a bunch of sum checks, and I think we know how to do sum checks very quickly nowadays. Okay, so another very interesting property of sketched code is something that we call piecewise distance. So I think in this Ligero style argument, we know how we encode, say, columns, then verifier sends some randomness, we fold, and then we have these spot checks. So verifier will send us a bunch of queries, which are like drawn from like uniform distribution of the block plan of the code we use, and then we just perform a lot of these spot checks. The idea here is that because of this very nice sketch structure, you don't need to throw these queries fully uniformly. So you can first check the bottom, the sketch part, with whatever code you're using, and after verifier checks that, only then it gets to checking the message part. And for this, it's very easy. You just prove that proximity gaps hold also for like affine subspaces. And this also improved a lot in our proof size, I think 20–30%. And there are also like some techniques how you can get very nice, nice distance amplification if you're happy to pay a little bit more in hashing. So yeah, we call it piecewise distance, and it's a very nice property of this code. And then in all these experimentations and trying to get the best of having a very fast prover but not paying too much on a proof size, being able to recurse, etc., we ended up with presenting this concrete instantiation, which is this alpha thing I mentioned, which is by how much we are compressing our message. We picked to be 8, and for this client-side applications and going to this 2 to the 30 to, let's say, even 2 to the 32 polynomials that you can nowadays actually very efficiently run on your laptop in a couple of seconds, we picked that 8 is kind of a sweet spot for having the best proving and proof size trade-offs. And then we used just rate 1/2 Reed-Solomon to encode this much smaller 8 times compressed sketch. Here, it's fully generic scheme. You can use RAA or Spillman, like whatever you like. It's just gonna, later you need to pay even with like potentially larger proofs or more complicated IOP for the code switch. So this instantiation is kind of balancing everything at the same time. Okay, we can speak more. I really think that we are having some improvement in how we should think about what is practical to do nowadays. Pure client side on our laptops that are not that expensive. We don't need GPU clusters. We don't need a large amount of compute to do very large polynomials and very large circuits. So all these codes are very SIMD friendly. So if you are careful with how you do like a little bit of assembly, a little bit of prefetching, and some CPU instructions, actually speed-ups are enormous. And also a lot of things we do nowadays, we want to benchmark with binary fields because they're very CPU friendly, which we show with the numbers before. And another, I think, very important part for the having systematic codes is that also on our current hardware, it comes with both CPU and GPU. So having a systematic code of high rate allows you to, while you're encoding, as we saw, you are just copying the message, which means the code is systematic. So what you can do is you can use either CPU or GPU based on which hash you want, and you can do this computation in parallel. And this is, you don't need to buy anything else to set up anything else. This comes on your chip for, like, so to say, for free out of box. So essentially, with the fast binary hashes we have now, you end up having zero cost of hashing almost. So that's also very, very neat trick that you can do with systematic codes. So there are a lot of things to explore here. Given yesterday Dan's talk and something that we know exists, which is this proximity gaps for LDPC codes. We know they work up to capacity, so there is like a lot of potential to actually further increase this, this 2 megabyte proof size that I showed, like by 3-4x. And remember, I showed you the proofs in unique decoding. We have also a bunch of Reed-Solomons there. So actually, when you use out-of-domain sampling, list decoding, you can drastically reduce these proof sizes. We already, just with a pure unique decoding, tested like recursion with Blake, Ketchuk, and it's very promising. You can like do this in a matter of a second, full recursion, and have ZK, have very small proofs. With proximity gaps, this is going to be a big win and super easy to have a full recursion. And here we use this like random LDPC codes. There is also potential to look into de-randomizing them using more structure graphs or matrices, which will actually allow you better IOP for matrix vector multiplication, because your matrix now will be not random, but actually structure. So you can exploit that further. And yeah, with that, I conclude the talk. Hopefully I'm on time. Yeah.
Thanks. I don't know much about the both Mini and Max. I only have a question about both theory, because when I first read the paper, I was very impressed, the idea, because I'm also working on coding theory. My question is for the distance. In the paper, it looks like the distance will always worse than the inner code and the outer code. I'm wondering, is that true, and why?
So actually, he asked about distance, right? Yeah. So as soon as you use any better code for the sketch, because of the piecewise distance, actually the distance will just depend on LDPC distance. So whatever is the LDPC distance, essentially that's going to be the distance of your code.
But in the paper, it looks like even with like LDPC, you need to divide with 1 plus another like positive value, right? It's still worse than LDPC even.
We can, like, I don't know what, so we can discuss, but no, it's, you first, for example, in our concrete instantiation, you have LDPC, and then you have Reed-Solomon. So you will first do queries on Reed-Solomon, which you can use out-of-domain sampling and like list decoding regime. It's going to be just a few queries, and then you make around 2,000 queries on the LDPC. But yeah, I'm happy to chat more if, yeah.
Hi, thanks for the talk. The sketch matrix H kind of looks like a code-based hash function when you compute the syndrome like that. Is it possible to push the parameters further by making computational assumptions on H as like a code-based hash function?
So here you have to be very careful, because you also need to use H in IOP. So H has to be like very structured. For example, in Reed-Solomon based, we have this rows of the encoding matrix being able to write it as a tensor product, which allows you to have a succinct and still fast prover. So H has to be LDPC. essentially, yes, you can be very creative with H, but as soon as you do something weird, you will have to pay at some other step of the protocol.
More questions? We have like a minute. Okay, let's thank the speaker again. Is the speaker?
Here we are.
Can you set it up with the mic?
Should I like use my laptop or should I just use a clicker or something?
Here we are. Come here. Yeah, but I'll leave the. Well, it's this way around your ears. And tell me if it's okay.
That's una scena bellissima.
Okay.
Oh, I mean, it's comfortable.
Okay. Now, let's just leave down your sweater or t-shirt as you prefer. Sì, è tutto lento, non al 100%. Well, we have to turn take it out. Oh, okay. Sorry. Okay. Now. And now put it or on your belt or pocket as you prefer. Just a second.
Check, vai.
Yep.
Can you talk?
Hello? Yep, okay.
All right.
Cool. So I can just use a clicker over there?
The clicker?
The clicker is
On the pod.
Oh, perfect.
Okay, our next talk, Anubhav will tell us about ERA, encoded P2 codes, and how to use them to get fast snarks.
Cool, thank you. Hi, my name is Anubhav. I'm a PhD student at the University of Pennsylvania. And yeah, this is going to be maybe, I guess, like the second core talk of the day. And it's maybe going to be like a little bit similar to Andre's talk, but maybe also a little bit different. Instead of, I guess, sketch codes, I'm going to be talking about like these things called error codes. Great. So first of all, what are snarks? Snarks are succinct non-interactive arguments of knowledge that allow a prover to prove statements to a verifier with a short proof. I'm not going to dwell too much on that. I'm sure all of you are familiar with them. And hash-based snarks are secure snarks in the random oracle model, which require like no additional assumptions. And they enjoy many, many nice features, such that they're plausibly post-quantum secure, they have no public key cryptography, they have fast provers, and they have transparent setups. And these are all nice, but there is one not-so-great feature that they have, which is that they have quite large proofs. So for example, if you look at the opening size of polynomial commitment scheme, for bullet proofs, which are not hash-based, you can get proof sizes that are like in the range of about 5 to 10 kilobytes. But if you look at the potentially like the state of the art in terms of proof size for hash-based snarks, you have stir and verb, which are in the range of 200 to 400 kilobytes. So there's a huge gap there. Great. There is another additional property that some hash-based snarks do exhibit and some hash-based snarks don't exhibit, which is field agnosticism, which is the property that provers can compute proofs over an arbitrary field of large size. And in particular, this means that the field doesn't need to be FFT friendly, doesn't need to have mean to be binary extension field, doesn't need to have like any particular structure. Great. So there are some hash-based snarks. Okay, so first of all, why do we care about field agnosticity? The main problem that we want to solve is non-native field arithmetic simulation. So for example, if you have a computation defined over a field FP, what's that? Oh, cool, thank you. So for example, a prime field like SCCP256K1, and say you have one gate in your computation, which is just like a simple addition gate, which is taking in two integers, two values A and B, and outputting their sum modulo P. Okay. And so, say now you have a snark prover that's defined under FQ, where Q is not equal to P. So now you can imagine this is like an FFT-friendly field. And what will happen is that in order to be able to simulate this one single gate of the computation over FP, you will have to convert it to a computation over FQ, and then you will, of course, like have this like a blow up in your circuit size. So in order to just simulate one operation that looks like A plus B modulo P, you would end up with like a bunch of gates that are modulo Q. Great. One of the applications of field agnostic snarks shows up in ECDSA verification. So we want to verify a large batch of ECDSA signatures, which is a computation that's defined over this particular curve. And there are numerous applications of this particular process, including ZK rollups, ZK bridges, anonymous credentials, you name it. Great. If we use something like Fry, Stir, Whir, then we would need to convert the computation to be over an FFT-friendly field. And this can lead to like a pretty big circuit size blow-up, like close to like 25x. And therefore, you would also have a prover time that blows up by 25x as well. Great. But the good news is that there already does exist like pretty good work on field agnostic snarks like breakdown and baseful. So why do we care about this? So out of like the many nice features that some snarks have, you might now, there are some, okay, sorry. The snarks that are not field agnostic, like Stir and Whir, have proof sizes that are in the range of 200 to 400 kilobytes. But if we want to talk about snarks that are field agnostic, like baseful and breakdown, then they actually have a bigger problem, which is that they have very large proofs. And these proof sizes can range from like 10 to 20 megabytes for baseful and breaking base, and 20 to 50 megabytes for breakdown and EA code-based snarks. And these numbers are for like fairly large instance sizes. So the question naturally is that can we get better proof sizes for field agnostic hash-based snarks? Amazing. Before we get to answering that question, we should go over some basic background about snarks, which I'm sure all of you are familiar with, but just for the sake of completeness, we'll go over it once. So snarks have a standard recipe from PIOPs and PCSs. You first have a polynomial interactive oracle proof for a relation R, where the prover is allowed to send polynomial oracles to the verifier. And a polynomial oracle for a multilinear polynomial in particular looks something like where the verifier can ask for the evaluation of this multilinear polynomial at any point, and then the prover is able to convince the verifier that, hey, this polynomial does evaluate to that value at this particular point. Great. And how do we instantiate these polynomial oracles? We do that via polynomial commitment schemes. So you have a prover and a verifier. The prover first commits to the multilinear polynomial M. Then the verifier sends back this evaluation point. And then they engage in an interaction where the prover proves to the verifier that the polynomial does evaluate to Y on Z. And the proof size of a snark is approximately equal to the proof size of the PCS. And the PIOP contributes very little to the proof size. And therefore, in order to get better proof sizes for snarks, we need to get better proof sizes for PCSs. OK. The hash-based PCSs have kind of a standard recipe from codes and IOPPs that we're also going to go over. So we have a multilinear polynomial M hat, and we want two ingredients. We want an error-correcting code with some encoding function, and we want an interactive oracle proof of proximity for the code. So we have a prover and a verifier. The prover first sends to the verifier this commitment, which is just the encoding of the polynomial under this error-correcting code. And what the prover really sends to the verifier is an oracle to this encoding. And then the prover and the verifier engage in an interactive protocol where the prover proves to the verifier that this W is indeed close to the error-correcting code C. And this is the interactive oracle proof of proximity. And during this interactive protocol, of course, the prover also sends more oracles. OK. And finally, after making some queries to the oracles, the verifier outputs accept or reject. Now, this whole scheme gives you an IOP for a polynomial evaluation claim. And once you instantiate the oracles via Merkle commitments, and then you apply fiat Shamir, you finally get a hash-based PCS. All good. Okay, so the two key metrics of a PCS that everyone cares about are prover time and proof size. The proof size in most hash-based PCSs in some ways kind of dictates the verifier time as well. So we can think of the proof size as being like a reasonably good proxy for the verifier time. So for the prover time, the two factors that contribute to the prover time are the encoding time of the error-correcting code and the prover time of the IOPP. For the proof size, you have the relative distance of the code and the communication of the IOPP. That are the two key contributing factors to the proof size. And so therefore, if we want fast provers and small proof sizes, what we need from the error-correcting code is fast encoding and large relative distance. And what we need from the IOPP is fast prover and low communication. Okay. And now we've shared all the background, we can finally, I guess, talk about our actual results. So we introduced a new family of codes called encode, repeat, accumulate codes, which are linear time encodable codes inspired from repeat, accumulate codes, which you might have seen in the recent work of Blaze. These are parameterized with a base code B, a repetition parameter R, 2 permutations, and a multiplication vector V. I will shortly get to what these individual things are and like what the encoding procedure looks like. And but what you should think of like this error-correcting code that serves as an input to our overall error-correcting code as just some code that has very fast encoding, but not maybe super great distance. So you can think of it as being, like for example, you could even use like Bolt, or you could use Lightning, which is the concurrent work with Bolt, or you could use Breakdown. And the reason we say that is because the results that we obtain show that the base code distance that you actually use for obtaining error codes doesn't need to be very large. It can be extremely small. But after you apply like all the operations that we apply to obtain our final error code, you can get distances that are like quite large. And in particular, if you have the freedom to be able to like really boost up your repetition parameter, then you can end up with the distances that are like quite high. Okay. Because of the strong distance guarantees of our code, we can already plug in our code into like old IOPPs, in particular the IOPP of Ligero and Breakdown, which uses interleaved code, to immediately get better proof sizes than like previously discussed IOPPs like Breakdown. So for example, this is like one small experiment with like a relatively short message length. But if you use a error code with repetition factor 4, then you can see that we get commit times and evaluation times and verifier times that are all very similar to Breakdown. But our proof sizes are like smaller because, and the proof sizes are mostly smaller because of like our increased distance compared to Breakdown. Breakdown, here we parameterize to have distance 0.1, but our error codes with rate 4, with R equals 4 have distance 0.228, so therefore they're able to get smaller proof sizes. Okay. One thing I want to very briefly mention is that conjectured error codes are the same as error codes, but we omit like a one multiplication step in the middle, and we can talk about it after the presentation if people are interested, because this is something that I'm quite curious about if this is possible to do, because if we are able to remove that step, then we'll have better encoding time, and then our codes will also be defined over rings, which is quite interesting. Okay. So we additionally also develop a new IOPP for error codes. And the new IOPP has these asymptotics, linear prover time, lambda log n query complexity, and small communication overhead, which then leads to a PCS with these parameters. And you might say that, OK, asymptotics don't really tell you the whole story. Like, it's really the concrete proof sizes that matters, because I promised to you that basefold and Breakdown and all of these hash-based PCSs have these concrete proof sizes in megabytes and stuff. So what about concrete numbers? And we also have some concrete results for a new IOPP. So first of all, state-of-the-art field-agnostic PCS for proof sizes is at least basefold and breaking base. And we compared ourselves to an optimized version of basefold. So it kind of turned out that when we actually started comparing ourselves to basefold, we found out that you can actually take the basefold's implementation and optimize it quite a lot for its proof size already, because through like kind of new techniques that have been, I guess, discovered in the last couple of years since basefold came out. And but even if you apply those optimizations to basefold, we're still able to get approximately 60% reduction in proof sizes for large instance sizes for comparable prover times. And in particular, you can see that like our proof sizes are at most 4 megabytes for message line 2 to the 32. And I want to say that the work is, of course, still not done because, as I mentioned to you before, non-failure agnostic snarks like stir have 400 kilobyte proof sizes. And so there is still like quite a big gap from what we achieve and what stir can get. And I will say that I believe that even though like we are able to get better proof sizes than basefold, there is still a good amount of work to be done on the IOPP front for our paper. And I think Giacomo and I both believe that we can do much, much, much better than what we already have. OK. So the remainder of this talk is now going to be like maybe quite different. I'm not necessarily going to talk about IOPs and snarks and things like that anymore. And I'm really exclusively going to talk about how do you actually analyze the distance of error codes. But you might say that, OK, Anubhav, you haven't even told me what the encoding procedure for error codes looks like right now. How can I do the distance analysis of them? And what I hope to be able to do through the remainder of the talk is, through the distance analysis, I want to be able to motivate what the encoding procedure should look like. Great. So the starting point of our codes are going to be binary RA codes, which are parameterized as 2 permutations and a repetition parameter R. And I'm going to have like a running example running on the side to demonstrate what's going on. So you have a message that's of length k. And the first thing you do is you repeat every element of W R many times to get that. And here R equals 2. Then you permute the resulting vector under this permutation to obtain like a new vector. After the permutation, you apply a prefix sum, which is what we call an accumulation operation, and to, in some ways, boost the Hamming weight of the vector that you have. So earlier, you can see there were only 2 ones in your vector, but now, because of applying this prefix sum operation, you are now getting a little bit extra ones. And then you permute it again, and then you apply a prefix sum operation again. And the resulting, and this entire code is called the binary RAA code. And this is going to be our starting point. And so the first question that we ask is, how do you actually compute the relative distance of RAA codes? And first of all, the relative distance of linear codes is the minimum relative Hamming weight of a code word. So we really don't have to worry about anything other than trying to see if we can boost up the number of non-zero entries in our code words. And there are only really 2 steps that boost the relative Hamming weight of our encoding, which are the accumulate steps. So these are the 2 steps 3 and 5 over here. And so therefore, these are the steps that you really just need to study in order to be able to analyze the distance of error codes. And how do you analyze the accumulate steps is what we will get to now. And our focus is just going to be for this talk going to be just on the first accumulation operation, because the second accumulation operation is a bit tedious to handle. OK, so how do you analyze the first accumulate step? You consider first one fixed vector W, and you split it up into weight of W plus 1 intervals. So what do I mean by that? So if, say, this is your input word to your accumulate step, then you divide it up into these intervals, which are designated by the non-zero entries of W. So the 0th interval ends just before the first non-zero entry. And the first interval starts at the first non-zero entry, goes up to the second non-zero entry, and so on. And now, when you apply the accumulation operation to this, you get a vector that looks like this. And you can see that the 0th interval now is off. Like it has zeros. The second interval is on, and the third interval is off. And you can imagine that in a binary case, this is kind of what's going to happen. You're going to have off, on intervals. And therefore, exactly half the intervals are going to be on, and exactly half of the intervals are going to be off. Exactly up to plus minus 1. So now, using the fact that W is uniformly random among the set of vectors with weight W, because we just applied the permute step just before we apply the accumulate step, we can show that the sum of the lengths of the on intervals is large. And this, in some ways, showing this is the main challenge for the binary case, and we're not going to dwell too much on this, because move on. And with this, you can argue that AW has large weight. OK. But the problem is that this is just one message, right? I said that, like, OK, we're considering one fixed vector W, and we're showing that, like, the output of applying the accumulate step to this W has large weight. In order to be able to actually show that your error correcting code has large distance, you need to be able to do this for all messages, right? Because the distance of a code is the minimum Hamming weight across all possible messages. OK, so how do you do that? First of all, the question that you need to ask is how many messages do you actually have, right? And only messages of weight W over R could have produced a vector of weight W after repetition. And there are only N over R choose weight W over R ways to choose such vectors, because these are just the non-zero entries that you would pick from N over R many indices. And once you know how many messages that you have, all you have to do is apply a union bound over them. OK? Once you have applied that union bound, you need to then finally apply union bound over all choices of the weight, and you're done. But the second union bound is somewhat insignificant because there are only N choices. And the real big number that you actually have to contend with is this, like, N over R choose weight W over R. So that's great. But what about large Q? So far, we have really been only discussing the binary case. So one of the not so great things about the binary case is the first sentence over there, that half intervals are on and half intervals are off, which restricts your distance, relative distance, to be at most 0.5. Just because of this property, and in general for, like, binary codes as well, you cannot have relative distances that are more than 0.5. But for larger Q, you can hope that this is not true, right? Because just as I was mentioning, in the binary case, you have this 0-1 flipping phenomena, that after an on interval, you always have an off interval, and after an off interval, you always have an on interval. But in the non-binary case, you don't have this. An on interval can be followed by another on interval. But the new problem is that now we have to apply a union bound over way more many vectors. So previously, all we had to do for choosing how many possible inputs you have is choose the indices and nothing else, right? But now, in addition to choosing the indices, you also have to choose what non-zero entry you're going to have in those non-zero indices. OK? This is a problem because Q can be potentially very large. And you can't just use the randomness of the permutation to be able to get a probability that's small enough to overcome this large union bound. So how do you handle this large union bound? And it's broadly a two-step analysis. We proved that, first of all, we proved that lots of intervals are on. We'll see what lots here means. And then we proved that the total length of the on intervals is large. And we have to apply this large union bound over both of these steps. And both of these steps require two different solutions. Like, there's no one single thing that actually helps you apply a union bound over both of these things. So the solution to the first problem is that we introduce a multiplication step. And in order to be able to union bound over all of these many things, we're going to use the randomness of this multiplication vector. And then for the second step, we actually don't even end up doing a union bound over all input messages, but rather something that or rather all input configurations. And we're going to see what configurations mean later. OK, so proving lots of on intervals. And how much time do you have?
7 minutes.
OK, so how do you handle the large union bound for proving lots of on intervals? We introduce a multiplication step, and we use the randomness of the multiplication vector. So what do I mean? We sample V uniformly random from the field. And I'll again have a running example on the side. And I'm going to demonstrate what the encoding now looks like. So now instead of a binary vector, you have a field vector. And the entire encoding procedure looks exactly the same, except after the permutation, you also do this element-wise multiplication by V. And doing this multiplication by V now actually helps you prove, like, something very interesting, which is that you can now prove that almost 1 minus 1 over r fraction of the intervals are on. So you no longer should do just half the intervals being on. You can now show that as r grows, the fraction of the intervals that are on also grows. And that is partly why when we saw the distances earlier in the table, we were able to get like larger and larger distances for larger and larger r. OK. So let's see be a constant that's like between 1 and 2. And we're going to the specific statement that we're going to prove is that 1 minus c over r fraction of intervals are on. W is an input to your accumulate step. And for each of the intervals, like we defined earlier, we define an indicated random variable, which is 1 if the ith interval is off, and 0 if the ith interval is on. I know it's kind of flipped, but bear with me. It's by design. And we assume that all the xi's are mutually independent. And this is, categorically speaking, not true. But you can assume that they're independent for now, because you can handle the non-independence with just some extra care. OK. So now this is what your input vector to your accumulate step looks like. You have 3 intervals. And the important thing to notice here is that if you want interval 2 to be an off interval, there really is only one value in the entire field that actually makes that interval off. Every single other value will keep the second interval on. And here, for example, that value is q minus 5. And the nice thing that we now have is that each non-zero wi is uniformly random. And why is that? Because we applied the multiplication step. So when we multiplied with this multiplication vector, we ensured that every single non-zero entry was a uniformly random field element. And therefore, we're able to get that the probability that any of the xi's is 1 over q minus 1. It's very, very small. OK. And finally, we want to show an upper bound on how many off intervals you can have. You want to show that the probability that you have more than CL over R off intervals is very, very small. And how do you do that? You apply a Chernoff bound. You have your expectation, which is L over Q minus 1, where L is defined as the weight of the vector. And if you just go through the steps, you can see that you will be able to get this expression, which, very importantly, is inverse exponential in Q. And because it is inverse exponential in Q, we can actually now do a union bound over all the many inputs that we described earlier. So we no longer have that problem that, oh, we have these exponentially many inputs, we can't union bound over them. But now we do have like this extremely inverse exponential probability of failure. Therefore, we are able to union bound over them. OK, so union bound over. I'm just going to walk over the union bound argument very quickly, which is that we have the failure for one message, looks like that. The number of messages look like that. You just multiply them together to apply the union bound, and you get that the probability of failure for any message is their product. This remaining stuff that is not a function of Q is completely insignificant if Q becomes large enough. And therefore, if you set, because C was greater than or equal to 1, the failure probability is inverse exponential in Q. So because you can see that the exponent of Q minus 1 is L times 1 minus C divided by R, and C is greater than 1. So that is the exponent is negative over there. And because this happens, if Q is sufficiently large, then all messages have 1 minus C over R fraction of on intervals after the first accumulate step. And the one small problem that is left to be solved is that the exponent of Q is this value, L times 1 minus C over R. So if C gets like very, very close to 1, as we usually set it to be, then it's not necessary that this exponent is very large, and therefore it's not necessary that this whole probability is very small, right? And this is finally where the final, I guess, change of our algorithm comes in, which is that we need the input weight L to be somewhat large in the first place. And how do we make that input weight somewhat large? We preface the encoding process with a very basic error correcting code. And so this is what you do. You just take what our previous encoding procedure was, and then you just prepend this like encoding procedure under B to get this WB. And now this is also why the distance of this base code B can be very small. Like in the table that we saw, we were using values that were like 0.001. And the reason it's like that small is because this weight or this distance shows up in the exponent of the field size. So you don't actually need it to be very large for the probability to actually become very small. And this is what our final encoding procedure for error codes looks like. You have M, you encode under a base code, you repeat, you apply permutation, you apply multiplication, you accumulate, you apply permutation, you apply multiplication, and you accumulate. And that's the entire encoding procedure. OK. How much time do we have? 1 minute. OK, great. I'm going to very, very, very briefly go over the second step, which is proving that the on intervals are long. And the rough idea is that you don't actually need to union bound over all the exponentially many different inputs, because you can club a lot of inputs together. And the reason for that is that if you have a weight, if you have a vector W, you can consider its configuration, which is just the same vector, but you replace all the non-zero entries with ones, and you replace the zero entries with 0. And we have already proven that a large fraction of the intervals of W are on with high probability. And now, if we somehow also prove that so now this statement is a little bit messy, so it'll take a second, that the probability that there exists any set of more than 1 minus C over R times L intervals that have small length is small. This entire argument can be shown with a counting argument, and we will not dwell on this. But if you are able to show this, then you are able to show a similar statement about W prime as well, where W prime is any vector that has the same configuration. So if the first statement is true for a W with a particular configuration, then the second statement is also true for any W with the same configuration. And therefore, this is the rough idea as to why you don't actually even have to union bound over that many inputs, and you are able to just union bound over these many configurations instead, which is not a function of Q at all. And finally, in order to obtain your final distance, you apply union bound again. You just solve for the largest delta, such that that particular expression is true. And that you can do with a simple binary search. That is your final output distance. And that is a very, very slight lie, because at the beginning of the talk, we said that we're only going to analyze the first accumulate step. So indeed, this is our distance that we obtain after the first accumulate step. What you get after the second accumulate step is, again, a little bit more complicated and tedious. And what I'm going to do is I'm not actually going to give you a mathematical proof of it. I'm going to give you a proof by intimidation. Yeah, OK. This is the last slide. OK. This is what the actual algorithm for the final thing looks like. It's like has a Hessian in it. It has partial derivatives in it. It's a whole mess. But the nice thing about this is that it's very easy for a computer to implement. You can just, we have a Python script for it that you can check out, where you can just plug in your desired lambda, your desired R, desired base distance, desired block length, desired field size. You can put in these 5 values. You just get your distance as your output. OK. But even though this does look complicated, I do want to say that it is conceptually very simple. And it is just very messy analysis and combinatorics that you don't have to contend with. And that is all I have to talk for today. Thank you so much. That's the paper. That's the distance analysis. And yeah, thank you for bearing with me.
A quick question while the next speaker sits up.
So I'm kind of curious, how should I be thinking of this distance amplification technique as compared to traditional kind of ABNNR and AL distance amplification at a high level?
Yeah, I think the main difference is that those techniques are explicit, right? They are deterministic. And this is a completely randomized technique.
No, so think of using a random expander there.
Oh, so I don't know if you can, I guess, necessarily look at applying a permutation and an accumulation operation as similar to applying an expander graph.
your thing takes an arbitrary code and amplifies its distance,
Yes.
right?
Yes.
That is a similar thing to what those
Yes.
classical transformations do.
Yeah, but the technique is like quite different, I guess.
Sure, but I mean, if tomorrow I have a code and I want to amplify its distance, which technique should I use?
Oh, in terms of practical numbers, if you really care about the numbers.
Yeah, how does it compare, in whatever way? Like,
I think the one thing that we did compare to was AEL. And the main problem I think that we ran into with AEL was that there was a very, very large alphabet size blow up. And I think when we tried to compute the exact numbers for it, if you wanted to get even like a distance of like 0.5, when you're amplifying from a distance of like say 0.01, like this blow up in your alphabet size was on the order of like millions. And therefore, it does not seem like something that you can. It seemed like very hard to make practical.
So there's an issue with concrete numbers.
Yes, concrete numbers.
But in terms of asymptotics or like general behavior,
With asymptotics, I'm not sure exactly what the gap is. Yeah.
So I have a question. So you showed that you did repeat, and then you multiplied, you permuted, and you multiplied by this V, right? But kind of, so whatever you analyze for that, you always can take a code word that is just, you divide by V, and like essentially, isn't it the same code?
What do you mean? Like you divide by V?
So you multiply it by V, right?
Yeah.
But okay, so if you take some code word and encode it, then so you multiply that state by V. Now take the same code word, divide it by V, right? And you should just like cancel that effect. So overall, can't you just get rid of this multiplication? Maybe I missed something with...
So I'm not sure why that would work exactly. Like, so you're saying that you encode, then you multiply, and then after you have multiplied, then you divide again?
Take two code words that they're the same, except one is a division of the other by V.
One is the division of the other by V.
Okay, let's take it
offline.
offline.
I see you're describing a bijection, I see. But yeah, let's take it offline. Yeah.
Yeah, but it doesn't seem to matter. Closer. Okay. Yeah, let's thank the speaker again. So we have one last talk. William, you're not ready yet?
Okay. Now, we're in this, like a crown. Tell me if it's comfortable. Maybe it's a little down here. Depends from your head. My head is very large. It's okay.
Yeah, I think so.
You're comfortable? Okay. Okay. Just a second. You don't have a beard, so it's easier. Well, now, take the cable and make it slip down your t-shirt on your back. If you want, I can help you. Okay, that's fine. Just a second. Let's see. What's that?
Okay, are you ready?
Just a second. Okay.
5, 4.
Okay, let's go. Now, put it on your belt or your pocket, as you prefer.
Sure. Oh, okay, it's working. Great. Okay.
Okay, William, go ahead. William's going to tell us about the tensor switch and what we can do with them.
Yeah, sorry, I have my own keynote, so okay. Yeah, so this is Tensor Switch. It's with Benedict, my advisor, as well as Giacomo and Ron, who's in the audience over there. Okay, cool. Let's get started. Yeah. Okay, so the main thing we're going to be talking about today is a polynomial commitment scheme. I'm sure we're all familiar with it, so I'll just go through the slides really quickly. So in a polynomial commitment scheme, there's some prover who wants to commit to some polynomial in what I'll call the commitment phase, and later in some opening phase, it will want to prove evaluations of the polynomial. Okay? A polynomial commitment scheme needs to satisfy both completeness as well as binding in order for it to be secure. Good. In this talk, I'll be interested in multilinear polynomials, but in fact, you can sort of use these techniques for whatever polynomial class you want. The choice isn't that important. Okay, and importantly, for polynomial commitment schemes to be useful, we would like both the commitment as well as the opening proof to be succinct, where we mean succinct in the description of the polynomial itself. Good. So it turns out that for practically efficient snark constructions, polynomial commitment schemes are a key component of how we build them. Specifically, if you take this object called a polynomial IOP, you can compose it with a polynomial commitment scheme, and then what you'll get out of it is a snarg. And moreover, PCSs are, I want to argue, are a key bottleneck of snarg efficiency. And in particular, by improving the efficiency of your PCS, you sort of directly improve the efficiency of your snarg. And one big reason for this is because a lot of the prover's sort of heavy work, such as cryptographic commitments, as well as encoding for hash-based snarks, all stem from the PCS. Okay, so I want to first present our results, and then we can talk about how we actually get there. So first of all, TensorSwitch is a polynomial commitment scheme for multilinear polynomials. Specifically, we're just going to let n be the size of the description of the polynomial, and this corresponds with a multilinear polynomial in log n variables. Okay. So if you look at TensorSwitch, first of all, it's instantiable over any field, which is sufficiently large for soundness to hold. So you should think of the field as being, say, 2 to the 128 elements. Okay, it's secure in the random oracle model. In practice, you would replace this with your favorite hash function. Okay, and the prover makes this many number of field operations as well as this much hashing, and the verifier does this many field operations in this number of hashing. Okay, so two things I want to point out. The first is that, at least for the purposes of this talk, this will constitute a linear time prover. We're sort of running in the order of the description of the size of the description of the polynomial. And for the verifier, essentially what we get is sort of the best possible verifier you can hope for, barring any sort of like fundamentally new techniques in how we design hash-based succinct arguments or PCSs, at least asymptotically. The actual constants, obviously, are still up for debate. More on that later. Okay. Let me also say that in terms of the choice of field, we can actually use a small field as well. You can sort of imagine that if we have a polynomial defined over a small field, we can always sort of lift it to some extension field. It's just that in this case, if we count the number of prover operations in terms of this small field, it might no longer be linear. Okay, and finally, I want to shout out this concurrent work with, I think it's Anupov, Matan, Pertusha, and Tushar, which basically get the same asymptotic results with some worse leading constants. Again, I'll speak more about the actual leading constants in a later slide. Okay, great. So I'm going to try to present our results in a sort of an idealized model. So we've seen throughout the day this sort of interactive oracle proof model. And similarly, I'm going to try to present our PCS as a sort of IOP. Okay. So in the commitment phase, we're going to sort of relax the assumption that the prover's commitment needs to be succinct. And instead, we're going to allow it to be long and also interactive, with the requirement that the verifier is only going to read a few of the prover's messages. Okay, and sort of this a few symbols of the prover's messages. And this transcript will sort of intuitively function as the commitment for the polynomial. And similarly, in the opening phase, we're going to allow this proof to be both interactive as well as long, so long as the verifier, again, only reads a few symbols from the proof. Okay. I'm going to call this an interactive oracle PCS. And in general, you can take such an interactive Oracle PCS and compile it to a hash-based PCS via standard transformations. Okay, so I included this shout out just because I think whenever I define this, like give a new acronym, I think there's sort of like a collective groan. Like we already have IOPs. Yesterday we talked about IORs. Why am I talking about this new thing in IOPCS? And for those of you who are more familiar, you might ask, why not just define this thing called an interactive Oracle proof of proximity and sort of be done with it? And what I want to argue is that actually the underlying protocol that we build to construct TensorSwitch is not an IOPP. Or more specifically, it can be used as an IOPP, but in order to get the best parameters possible, we're going to sort of move out of that model and build something which I sort of want to abstract as just an information theoretic polynomial commitment scheme, and hence interactive Oracle PCS. But again, this is sort of just like a name for the sort of information theoretic object that we're targeting. Okay, so previously I presented TensorSwitch as a hash-based PCS. Now I'm going to sort of unwrap it a little bit and present TensorSwitch as an interactive Oracle PCS. And you'll see that sort of all of the numbers that I gave in the previous slide follow as a direct consequence of the numbers I'll give here, along with the standard hash-based transformation. So first of all, let me just fix a linear code with some rate rho and distance delta, or I should say MCA distance, where MCA is mutual correlated agreement. Okay. I'm also going to consider its encoding rate tau. So you should think of, for a linear time encodable code, tau is some constant. For Reed-Solomon code, assuming that it's sufficiently nice, tau would be like log n. Okay. So if you look at TensorSwitch's underlying IOPCS, the prover performs this many number of operations. The first line sort of corresponds with encoding with the tensor code, and then the second line is any the additional arithmetic operations the prover makes. Okay. The overall Oracle length is again linear in n. Okay. On the verifier side, it's going to make a strictly logarithmic number of field operations, and actually it's going to make on the order of the security parameter number of queries. Okay, where here I'm giving the leading constant. Actually, for all of these parameters, I'm giving the leading constant just to be as precise as possible, hiding lower order terms. Okay, so assuming that we pick our code such that the encoding rate as well as the overall rate of the code is constant, then this is a linear time prover. And assuming that we pick the code so that its MCA distance is constant, then we get a query optimal verifier, at least asymptotically speaking. And one thing I want to point out is sort of that the leading constant that we get for this number of queries that the verifier makes feels very natural to me. It sort of corresponds with using a tensor code where the underlying base code has distance delta. Okay. Good. So one small note about extension field arithmetic. So previously I mentioned that you could always sort of run TensorSwitch over a small field so long as you're willing to lift it to an extension field. I want to briefly remark on what the parameters look like in this sort of setting. So let's say I let f be the small field, and now I'm going to write k to be the large field, which has like 2 to the 128 elements. This is what TensorSwitch's prover looks like now. I want to highlight that actually a lot of the operations still remain in the base field. So for example, encoding is still going to be done over the base field. And actually, the only operations that the prover does over the extension field is just these 9n big field operations. And I think one interesting consequence is that actually in TensorSwitch, if you're in sort of this extension field regime, the prover is actually only hashing a sublinear number of extension field elements in the opening proof itself. And just to contrast with sort of previous hash-based succinct or hash-based PCSs where they do roughly linear. I think this is just, I guess, an interesting feature. Okay. So let's move on to sort of a technical overview of the TensorSwitch's IOPCS. First, I just want to briefly review some background about codes. So throughout this talk, I'm just going to fix some linear code C. Okay, you can think of C as just being a collection of code words in some ambient space. The distance of this code is just going to be the smallest distance in terms of Hamming distance between any two code words. I'm going to define the unique decoding radius to be the distance over 2, such that if I pick any point in the space, then there's only going to be at most one code word which it decodes to. So we'll say that any point uniquely decodes to some corresponding code word, or perhaps none at all. Okay, and then I also need to define what a tensor code is. Okay, so sort of this is how a tensor code works. Imagine that you sort of arrange your message that you want to encode as a k by k matrix. Okay, so if your overall message is length n, then the number of rows and number of columns is going to be roughly square root n. And the idea is that a tensor code is going to first encode the rows using your base code C. Okay, this basically gives you a k-wise interleaved code. But then it's also going to encode the columns as well. And so what we'll end up with is like a larger square matrix. Okay, and this is a tensor code. In general, you can also use tensors where you use like a different code along each dimension. So I encode horizontally with the code C1, and then encode vertically with the code C2. For simplicity in this talk, I'm just going to focus on the case where the codes are identical. So this is just like a square tensor code. Okay, so let me try to establish our goal. So roughly speaking, the prover wants to commit to some vector m, and we're later going to prove linear evaluations of m. So m dotted with some other vector w, and we're just going to require that w is sufficiently nice. So what do I mean by nice? Intuitively, you can think of it as having sort of a sparse or a succinct description. And for example, this subsumes polynomial evaluations as a special case. So you can think in polynomial evaluation, you're just doing a linear evaluation where this weight vector is sort of just the monomials like 1, x, x squared, x cubed, so on. Okay. Okay, and then I'm going to let k be square root n. So this is going to be the dimension of our square matrix, the number of rows and the number of columns. Okay, and the commit phase is pretty simple. To commit, all the prover is going to do is going to interpret its vector m as a matrix, just reshape it, and then encode with the tensor code. Good. So, an honest prover, we can expect to always commit with an actual tensor encoding. But obviously, in reality, we don't expect like a dishonest prover to necessarily commit to a tensor code. And so we need to handle this situation. Right, so let's say you just have some arbitrary matrix F. It could be a tensor code word, it might not be. We're going to sort of define an underlying message for which it commits to in sort of a two-step fashion. So first, let's say you had this matrix F. We can sort of, corresponding to F, define this matrix G, which is the column-wise unique decoding of each column of F, right? Okay. Now, given this matrix G, we can again consider the row-wise decoding of G using the interleaved code, right? So in the first case, suppose that G is actually close to some interleaved code word. Okay. So in particular, if you just correct a few columns of G, then you'll obtain an interleaved code word, and then you can perfectly decode to obtain some message matrix M. Okay, so this is the good case where we say that F commits to M. Okay. Later on in the opening phase, we're going to basically check our evaluation claims against this matrix M. There's also the case where G simply does not decode to anything for some reason. Maybe it's just far from any code word, any interleaved code word. In this case, we're going to say that this commitment is malformed. There's no underlying committed message. Okay. So for today, I'm just going to focus on handling case 2 and showing how the verifier can actually reject case 2. It sort of turns out that this is the main difficulty for the IOPCS. Great. So how do we do this? Well, I'm going to first sort of give a base protocol, which I'll use as sort of a launching point to obtain our tensor switch to obtain tensor switch. And that's going to be the Ligero protocol for testing proximity for interleaved code words. Okay? So for the moment, assume that instead of having access to F, actually the verifier had access to G, sort of the claimed interleaved code word. And what the Ligero protocol basically says is, OK, the verifier is just going to take a random linear combination of the rows. The prover is going to compute the corresponding combination of the message. OK, it's just going to send it over. And then the verifier is just going to sample a random column and then check that the combination that the prover sent over is consistent with the column that it picked. Okay, and then you can sort of soundness is based on proximity gap of the code, and you can just repeat this a bunch of times in order to get a good soundness error. Okay, so this works. I just want to point out there's basically two issues with this approach at a high level, or I should say there's one issue and it shows up at two places. Basically, the issue is that the verifier, in order to compute this check, needs to make a lot of queries, in particular, roughly square root n many queries. And the reason why is basically, in order to compute this left side of this inequality, encoding this message that the prover sent and looking at the if symbol, it needs to read the entire message. Okay, and again, this is of length square root n. And in order to compute the right side of the equality, computing this random combination of the column, again, it's going to need to read the entire column. So that's, again, another square root n many entries. Okay? And so really, you can think of TensorSwitch as sort of taking this base protocol and upgrading in a way such that the verifier no longer needs to make square root many queries. Okay. So here's our approach. It actually is pretty simple. Recall that actually instead of working with this claimed interleaved code word G, we're now working with sort of F, which you can think of as the column-wise encoding of G. And analogously, our goal is basically to test if F decodes to some bad G. Okay, and by bad, I just mean what the Ligero protocol was testing, right? If G is far from the K-wise interleaving of C. Okay, and the protocol sort of roughly follows Ligero. So the verifier is again going to pick the random combination of rows. The prover is going to sort of just simulate the Ligero protocol in its head. And here I just want to depart a little bit and introduce some abstraction, which I find useful, and I'll call a linear oracle. So in a linear oracle, okay, let me back up. First of all, in a typical sort of interactive oracle setting, you imagine that the prover's messages are long, but the verifier will only make a few queries to some points in the oracle. For a linear oracle, you can imagine that the verifier is able to make a linear query across the entire oracle. So it can specify some weight vector for which it learns the inner product with the oracle itself. Okay, so imagine that we're now in some sort of linear oracle setting. The prover is going to send this combination, this Ligero combination, as a linear oracle instead of just a normal point oracle. Okay. The verifier, again, is going to sample a random column, as in Ligero. And the prover is going to now send the column corresponding to G, which the verifier would have checked in Ligero. Again, this is as a linear oracle. Okay. And now we're going to basically test consistency between this column that the prover sent, which it claimed to be the corresponding column of G, against the encoding of G, which is F, at the same column. Okay, and this is done by sampling a random row of F. Okay. And now the verifier is just going to check the Ligero check, as well as this consistency check between the column that the prover sent, as well as the original matrix F. Okay, and importantly, now that these two oracles are linear, actually computing this is very cheap. The verifier only needs to make roughly 3 linear queries total, so 1 to combo and then 2 to call, as well as a single point query to F, in particular the coordinate at the jth row in the ith column. Okay, and again, if you want good soundness error, then you just need to repeat this security parameter a number of times. Okay. Good. So this is sort of what the current protocol looks like at a high level. We're not done yet because right now we're sending these linear oracles. And so what we're going to do now is a very natural approach, I think. We're just sort of going to compose our protocol with itself. So remember, our commitment scheme sort of supports linear evaluations. So what we're going to have the prover do is, instead of sending these linear oracles in the clear, we're actually going to use our own tensor switch IOPCS and commit to them with like a smaller tensor code. Right? So now these linear oracles are like square root in size, so we can use a much smaller tensor code, commit to them, and reduce any of the linear evaluations we wanted to check by running this, essentially our IOPCS again. And we'll just do this over and over again with smaller and smaller tensor codes until it's at a size that we can just open ourselves. Okay. And this process needs roughly log n many compositions until we reach a constant size. Okay. You can also think of this as code switching. Essentially, we're switching from sort of the base code for the original tensor code to some smaller tensor code. That's like another way of thinking about it. Okay. Good. So I just want to say something about how we get our sort of optimal query complexity. This part is pretty easy, actually. So first of all, we need to improve our sort of analysis that I gave here from the unique decoding regime to the list decoding regime. It turns out this is quite complicated, a lot more complicated than in other sort of PCSs like WER or like WER or Ligerito. But once we do that, it sort of becomes fairly straightforward. The main idea is that since we're sort of reducing this problem size by so much, like from n to square root n, we have a lot of room to play with how we select these additional codes further down the recursion. And in particular, we can set them so that they have really good distance, and essentially we don't have to even think about the queries that the verifier is making to these subsequent recursions. So this becomes the dominant cost. There's this like leading factor of 2, which we can also improve to essentially 1. Okay. Cool. So I just want to conclude. This is what tensor switch looks like as an IOPCS. And let me just give some open problems. So the first is, we have the sort of optimal asymptotics. Obviously, the constants are, again, still up for debate. In some ways, I like these constants. They seem very natural for using a tensor code. So in particular, the prover seems to necessarily need to make this number of field operations to encode. And it seems like the verifier also needs to necessarily make this number of queries if the prover is committing with a tensor code. So maybe tensor codes are sort of done here, and we might need other techniques to get better leading constants. Another thing is, can we get faster proving over small fields? So I sort of gave one example where tensor switch improves over previous work in this sort of small field regime, which is that it only needs to hash a sublinear number of extension field elements in the opening proof. Can we do better than this? I think there's a lot of work to be done here as well. Okay, thank you. This is our paper.
Yeah, we have time for questions.
So the new analysis is based on MCA, which means it would be a little bit hard to extend to like a linear encodable code-based scheme, right?
Say it again?
Because now the new analysis is based on MCA, so would it be a little bit hard to extend to like a linear encodable code-based scheme, right? Because we don't have MCA until so far.
I think we have some generic results. Obviously, it's not like not as good as Reed Solomon, but
yeah, but once we have the MCA, yes. But, yeah,
sure.
I don't say your reduction is issue, but just we don't have MCA until so far.
Okay.
Yeah, thanks.
Thank you for the talk. So yesterday in the open question session, it was mentioned that we don't have straight line extraction for these tensor constructions. Can you sort of tell us a bit why that was hard to get, or why we're
Yeah,
struggling
yeah,
to do
okay.
that? Thanks.
Good. Actually, I forgot. I was like editing my slides yesterday, and I forgot to. I wanted to add that as another open question. So yes. So let me just repeat the question. So, or actually, wait. You had the microphone. So for a lot of the IOPs, based on interleaved codes, we do have straight line extraction. Actually, this wasn't even known for, like, this was, yeah, like a few years ago, this was not known either. And sort of, I think the intuitive reason why we have it is because we sort of interleaved codes play nicely with proximity gaps and like this mutual correlated agreement notion. Sort of like the first like high level explanation is that we're using tensor codes instead, for which it doesn't play as nicely. And okay, maybe I'll give like a sort of second layer explanation. Essentially, when we if you can think of the row code as being like what Ligero uses, and the column code is what we add on, we're actually using the fact that the row code has sort of mutual correlated agreement. But in our analysis, we're not actually using mutual correlated agreement or proximity gaps for the column code at all. So that's where the difficulty stems in. So actually, if you instantiate a protocol with a efficiently error-correctable column code, but like whatever your favorite linear time encodable code for the row code, it would actually be straight line extractable. It's the row code needs mutual correlated agreement.
Yeah.
The column code does not.
So the row, okay, yeah.
So we're not even using proximity gaps for the column code. So I think it seems hard to me to make this specific protocol work, like get straight line extraction. It doesn't seem inconceivable to me that you could sort of maybe construct a similar protocol, maybe slightly more complicated, that sort of leverages mutual correlated agreement along both axes, and then maybe you can get straight line extraction. I don't know.
Quick follow-up. So what properties do we need from this column code, and can we
That's good distance.
use something other, like something more efficient? Sorry?
Well, you're asking what properties we need from the column code?
Yeah, and
Right now, it's just distance.
just distance.
Distance. And well, obviously, we want good rate as well. Yeah.
Okay, let's thank the speaker again. This ends the session. We have half an hour break, and go get coffee.
Thank you very much. sta più di metà va bene. Sì, mettiamoglielo dopo. In teoria un pochetto sì, però...
Yeah. Right.
Thank you for coming back after lunch. I hope you had a nice lunch and nice chat with your fellow colleagues. Are we ready to start?
I think if my slides on there.
Just a second.
Hello? Yeah, it's working.
That's okay. Speak now.
1, 2, 3, 1, 2, 3.
Now it's okay. Okay. I don't know what's that. Okay.
All good? Everybody can hear me? Okay, so welcome back. Another great session ahead. Some foundational work and some more practical results. We are going to start with Anubhav, talking about foundational work on trade-offs between time space for sum checks. So please go ahead.
Awesome. Thank you so much. Am I ready to go? Oh, hi. Welcome back, everyone. So now I'll be talking about like some time-space trade-offs for sum check. And so this talk is going to involve like an upper bound proof and a lower bound proof. So hopefully there's going to be something for like everyone in this talk. This paper appeared at ECC 2025, and it's joint work with the wonderful folks at EPFL, ETH Zurich, and Penn. Oh, the clicker I don't think is. I think it's not configured to the slide. Okay, thank you. Okay, again, snarks are succinct non-interactive arguments of knowledge, which help a prover convince a verifier for a statement with a short proof. And recent work on snarks uses sum check as a building block, as all of you might already be familiar with. And this appears in all sorts of like different ways, whether that be through streaming snarks, ZKVMs, memory checking arguments, all sorts of different PIOPs, you name it. So therefore, the space-time efficiency of snarks crucially relies on the space-time efficiency of sum check provers. And what is sum check? Just to recap very briefly, given a multivariate polynomial f and a target sum sigma, a prover convinces a verifier that the sum over the Boolean hypercube of the evaluations of that particular function f equals sigma. Existing sum check provers already exist, and they're already very, very efficient. So let's talk about like two of them. They are the folding-based sum check of CTY11 and the locks-based sum check of CMT12. The folding-based sum check is very, very fast. It is like optimal linear time, but it suffers from the fact that it requires like linear space, and it's like you use a lot of space. On the other hand, the log-space sum check has this additional log n factor in time, and therefore it's like concretely also like quite inefficient. But it is space optimal. The only thing it really stores is the random challenges that the verifier sends, and really nothing else. So naturally, the question is, can we get prover algorithms which have time and space that is somewhere in the middle? Okay. And additionally, can we also prove lower bounds for space-time trade-offs? And an additional question can be that, can we get better trade-offs by departing from the interactive proof model, by just changing how the sum check protocol is implemented? Okay. For the remainder of this talk, our model of time is going to be number of field operation, and our model of space is going to be the number of field elements that are stored by the prover. Great. So just to summarize our results, we propose sum check. We both propose upper bounds and lower bounds for both sum check over multilinear polynomials and product of multilinear polynomials. Product of multilinear polynomials is a case that covers practically all like relevant applications for snarks. And in this talk and in the paper, we mostly focus on product of two multilinear polynomials, but the results extend reasonably well to more polynomials as well. So for multilinear polynomials, we get that if you have space that's n to the 1 over k, then you require time that's only kn, where k can be any parameter that you want to choose. And for our lower bound, we get the fact that if your space is at most n to the 1 over k, then you must use a time that's at least kn. So our sum check algorithm for multilinear polynomials is in fact tight. Great. On the other hand, for product of multilinear polynomials, we get this additional log n additive factor in the time if you have the same space n to the 1 over k. And that might seem like kind of strange, like why do you have a log n factor out of all the possible things you could have? But we show that this log factor is in some ways inherent. That if your space is at most n to the half minus epsilon, then you actually do require n log n time. So one example of the upper bound is that if you set k equals 2, then you get squared space and n log n time. And just one additional thing, that this lower bound is conditional on some natural conjectures that we make about the multiplication of multilinear polynomials. Because if it were not conditional, and in fact, for example, if you had matrix multiplication that you could do in n squared time, then this lower bound would not hold. And in fact, you could get an upper bound for product of multilinear polynomials that matches the one for product of multilinear polynomials that matches the one for multilinear polynomials. Great. And additionally, we also answer the third question raised on the previous slide, which is that in the PIOP model, where the prover can now send polynomial oracles in addition to just like plain text messages, you can then achieve n to the 1 over k space and k plus log star n time. So as opposed to log n, you get log star. But we won't discuss this in today's talk. So we kind of want to, I guess, summarize our results in this, I guess, graph for our product of multilinear polynomials. So first of all, the CTY11 result can be seen as linear space, linear time, and the CMT12 is n log n time, log n space. And then additionally, from our result, we get like two maybe interesting parameterizations, which are that you can get square root n space and n log n time, or you could get log n space and n log n over log n time. So that strictly improves upon the CMT12 algorithm. And our upper bound, of course, can be interpolated through all possible values of k that you might want to set. And then our lower bound is also starts, I guess, becoming more and more relevant when your space is smaller than square root n. And we also show that you can then bypass this lower bound in the PIOP model if you're willing to send polynomial oracles. OK, fantastic. OK, just to recap. So these are the final results that we get for the asymptotic results that we get for sum check over product of polynomials. Now you might say that, OK, I have this like O of n log n plus k. If I really want to implement this sum check, if I want to implement the sum check prover, I don't just care about like big old time complexity, right? I actually want to figure out, you want to be assured that I'm not hiding like 1,000 factor in like the big O notation over there, right? So therefore, we also implemented this protocol, and I think we get like some reasonable numbers. So we implemented over like a 128-bit field, and we set n to be 28. And in that case, what happens? First of all, the folding-based sum check, as you can expect, is very fast, but it takes like 7 gigs of memory. The log-space sum check is very slow, but it takes basically no memory. And for a new result, you can parameterize it in a number of ways. So one way is if you set k equals 2, then you can get a time that is reasonably close to the folding-based sum check. So you have an overhead of about like 1.85. But your memory requirement goes down by like a factor of 120. And then if you're happy to pay in with a little bit more time, then you can, of course, change the parameterization and set k to be equal to 4 and get memory that's like very, very close to the log space sum check and still be way faster than what the log space sum check gives you. OK. So now we'll just discuss some background before we move on to our constructions and our lower bounds. First of all, OK, what are multilinear polynomials? They are polynomials where the degree in each variable is at most 1. they have a very nice Lagrange basis representation, which means that they can be represented uniquely with their evaluations over the Boolean hypercube. And in particular, they are the random linear combination of their evaluations over the Boolean hypercube, where the coefficients are these Lagrange basis coefficients. And these Lagrange basis coefficients are, of course, very efficient to compute. And the model for our upper bounds that we want to consider in this work is the streaming access model, where the input to the prover is a stream to the evaluations over the Boolean hypercube of this polynomial. So at first, like, you have a pointer that's like pointing to the 0th evaluation over the Boolean hypercube. Then you press next, and you get the next evaluation. You press next, you get the next evaluation, and so on. That's our model. OK, and we'll briefly recap what sumcheck is. We want to prove that the sum over the Boolean hypercube is equal to sigma, and the verifier has oracle access to the polynomial. In the first round, the prover sends this h1x1 polynomial, which is the first round polynomial. And it is important to, I guess, like, remember what the structure of this round polynomial looks like. So what's happening here is that you're summing over all the last n-1 variables, and you're only setting the first, you're only keeping the first variable as a variable. OK. Then the verifier performs the check and sends back a random challenge. And the next round, now the prover, for the second round, prover defines a new round polynomial, where the first variable is now set to the random challenge that the verifier sent. The second variable is still now a variable, and you sum over all the remaining n-2 variables. And then this pattern continues. And so this is what broadly the sumcheck protocol looks like, and these are the checks that the verifier performs. For the purposes of this talk, we're not going to change the sumcheck protocol itself. The sumcheck protocol is going to remain the exact same. What we are really concerned with, how the sumcheck prover is implemented. So the questions that we actually want to ask are how the prover actually computes these round polynomials and how it maintains its internal storage across these different rounds. OK, so we'll go over the prover algorithm for multilinear sumcheck, which, as you might recall, requires only linear time if you set k equals 2. And the thing that we'll do here is that we'll try to do something that's kind of in the middle of the folding-based sumcheck and the log-space sumcheck. In the folding-based sumcheck, the only time you actually read the input stream is in round 1, and that's it. And because you are OK with getting linear space in that algorithm, you just store these things called folded polynomials. And therefore, you just never have to read the input streams ever again. You just read them in round 1 and never again. On the other hand, log space algorithm, it's the other end of the extreme. You read the input streams in all n rounds, and you store nothing at all except the random challenges. So we want to do something in the middle. So the most middling thing, I guess, you can do is read input streams in 2 rounds, which are rounds 1 and the middle round, n over 2. Now we will use square root n space, and what we will store are these things called sums of subcubes, which I'll get to in the next slide. OK, so what do you do in the first n over 2 rounds? The high-level idea is you want to be able to store all the necessary information in round 1 that allows you to compute the round polynomials of the first n over 2 rounds. OK, so to that effect, we introduce a notion of a generalized round polynomial. So in the regular round polynomial, what were we doing? We were just keeping one variable a variable, and we were summing over everything else. Now, we're going to keep the first n over 2 variables, and we're going to sum over the remaining n over 2 variables. OK, and the reason this is nice, this is a nice abstraction, is because say you are able to compute and store this polynomial somehow, then you can plug in any value of R1 through Rn over 2 that you see later to be able to compute the appropriate round polynomial. And therefore, you would not need to read the input streams in rounds 2 through n over 2. And the next time you will read the input stream will be in round n over 2 plus 1, and you'll be happy. OK, but the question is now, OK, how do you actually compute and store this generalized round polynomial? And we will use our best friend for this talk, Lagrange interpolation, which is that you expand this function out into its Lagrange representation, and then you just change the ordering of the sums, and you get this particular expression. And this expression is particularly nice because it has this like kind of structure where only the outer sum depends on these variables. You have this outer sum and this inner sum. The inner sum does not depend on x1 through xn over 2 at all. It's just like a function of the polynomial. It is not a function of the random challenges that you have not seen yet at all. So because it's not a function of those things at all, you can immediately just right now store them. Okay. And if you do store them, which means that you're storing these expressions for all x in 0, 1 to the n over 2, that means that eventually once you get R1 through Rn over 2, you can plug it back into this expression and compute the appropriate round polynomial. And so how much storage have I actually used here? I've only used square root and space, which is equal to the n over 2. Okay. So that's what you do for the first n over 2 rounds. What do you do for the last n over 2 rounds? You do something very similar. In round n over 2 plus 1, you compute this new generalized round polynomial where the last n over 2 variables are variables, and the first n over 2 variables, you know what the random challenges are now. So you can just set them to be R1 through Rn over 2. Okay. And again, you would expand this through Lagrange interpolation. You will get that expression. And you can then see that one value of this expression can be computed in only square root n time. And there are square root n many values that you need to represent this polynomial. And therefore, computing it in total would take linear time. And of course, storing it, of course, only again takes 2 to the n over 2 time, which is equal to square root n space, which is the same as before. So in both rounds, we have computed like some storage. We have only used square root n space so that you can then later on compute the round polynomials for the next n over 2 rounds. And that is the entire algorithm for the multilinear sum check. Now, you might be asking, OK, where does the log n show up in the sum check for products? So in today's talk, I'm not actually going to go over the product sum check protocol. Because I want to also go over the lower bound. But I want to give you some motivation for like how this log n shows up and why it's kind of necessary. So in multilinear sum check, what we saw was that we could get away with 2 passes in rounds 1 and n over 2, and that's it. And each pass required linear time. So let's see what happens if you just like try to do a product sum check for k equals 2, and we make passes in only rounds 1 and n over 2. So in that case, if you try to do that, then you would have to compute this generalized round polynomial, which now looks like instead of just a sum over m1s, now it's a sum over products of m1s and m2s. And these m1s and m2s are themselves multivariate n over 2 variate polynomials. And in general, multiplying polynomials is a hard problem. Like we do not know a linear time algorithm for it, right? And that is sort of why if you were to try to do this and like store this round polynomial in one go, you would need way more than linear time. And you, of course, will not get overall linear time because you're just been spending more than linear time in just one single round. OK, but what you can do is you can change your algorithm to make passes in only rounds 1, 2, 4, 8, essentially powers of 2. And then it kind of turns out that even if you do this polynomial multiplication naively, without like using any fancy FFTs or anything like that, even if you do it naively, then you would only require linear time in each such round. And how many rounds are there? There are log of little n equals log of big N many rounds. OK, so that's pretty nice. But in reality, when you actually implement the protocol, it doesn't, choosing like powers of 2 is not necessarily like the most optimal thing to do in terms of like concrete time. So in these numbers that I showed you at the beginning of the talk, these numbers are not obtained from making passes of the input streams in round 1, 2, 4, 8, and so on. In this case, we made rounds, we made passes in rounds that were like 1, 2, 3, 5, 8, 13, which, I mean, might look familiar. I mean, it's like the Fibonacci sequence, one of the most famous sequence of numbers. Is that a coincidence? Yeah, it is actually a coincidence. There's nothing fundamental here going on. And because we could have honestly just chosen like a slightly different set of rounds if we wanted like a slightly slower prover and we want our memory budget was slightly lower. Okay, but the key takeaway from, I guess, this slide is that our algorithm can be parameterized based on our specific memory budget. So the way you would choose what rounds to actually make passes in is that you would specify some memory budget. You would have like some 20 megabyte memory budget, and then you can figure out what these rounds, what the optimal set of rounds to make these passes are from your memory budget to optimize your prover time. Okay, so that's all I have to say about the upper bound. And now I want to talk a little bit about the lower bound for multilinear sum check. Okay, so as lower bounds usually go, I think sometimes you need just like a little bit of time to even explain what your result is. And that is what this slide is going to do. It's just going to explain what the result is. So the model that we used for our upper bound was streaming access to multilinear polynomials. For our lower bound, we actually want to do something stronger. We want to prove lower bounds in a random access model. Mainly because if we only proved lower bounds in like this particular streaming model where we are assuming that, oh, our evaluations are arriving to us in like a particular order, then it's possible that we are not ruling out the existence of algorithms that maybe get their evaluations in a completely different order, and maybe that's like fine for us. So we want a very general lower bound so that we can show that there's no trickery you can do behind like changing the ordering of your input or anything like that to get a better algorithm. Okay, another plus point of our algorithm, of our lower bound, is that the lower bound is not just on the number of field operations that the prover algorithm has to make, but it's on the number of input accesses. So now because we have specified that we are in the random access model, we can talk about, oh, this is like the number of input accesses that the prover makes throughout its execution. And of course, the total time is going to be like strictly more than the number of input accesses that the prover makes. The only, I think, negative point about this lower bound is that you have to kind of assume that the prover is non-adaptive with respect to the polynomial and random challenges. So non-adaptive here just means that whatever accesses that the prover is making to its input don't change with what random challenges it sees. And this is maybe not the worst thing in the world because we already kind of do know that like all existing sum check provers like ours and the ones that came before us are non-adaptive. And at least to me, like right now, it does not seem that there's anything you can really do with an adaptive sum check prover, but maybe I'm wrong and I would love to be wrong. Okay. So the lower bound that was stated in the results section was that if you have space that is n to the 1 over k, then you require time that is at least kn. This expression is kind of unwieldy, but it can be transformed into this very simple and clean expression, which is that t log s is at least omega n log n. These two things are equivalent. And then furthermore, you can kind of rearrange things to just say that t is at least n times log n over log s. Okay? So if you want to prove like that t is at least n times log n over log s, then one thing that you can try to show is that you need to read at least omega n input elements every log n over log s many rounds. And if you prove that, then of course you will end up with the lower bound. Fantastic. Now we have to introduce the notion of the prover, the sum check prover, as in some ways a multi-party prover. What do I mean by that? So right now we have been thinking of the prover as this like monolithic thing, which is which exists like all throughout n rounds of the sum check protocol. It has some internal storage. It receives the input, which is m, and it computes the round polynomial in each round, and it updates the storage in each round. But we should not necessarily think of the prover for the purposes of the lower bound in this way. We should think of it as n different provers, where n is the number of rounds, where you have one prover for round 1, and one prover for round s plus 1, where this little s is defined as log of big S. Big S was our space bound. And then so on and so forth. So you have 2s plus 1, around 2s plus 1 prover, and so on and so forth. So in total, you have log n over log s many parties that you're interested in. And because the prover is ultimately like just one party, what we can actually try to say is that the communication between the round 1 prover and the round s plus 1 prover must be at most s if the overall space bound on the prover is s, right? Okay. And that also goes for the other pairs of rounds as well. And what we can now, I guess, simplify our goal to is that we can say that if we just look at this communication problem between the round 1 prover and the round s plus 1 prover, then we want to show that if the communication from party 1 to party 2 was at most s, then party 2 must require, make n reads to the input in order to maintain completeness. Okay, and we'll rename these two parties, as in like all communication protocols, to Alice and Bob. Okay, so now you have a round 1 prover, which sends over some storage over to the round s plus 1 prover, whose inputs are the input polynomial m, the target sum sigma, the random challenges it has seen so far, so R1 through RS, and this storage that the round 1 prover is sending to it. And its goal is to now compute the round polynomial, which is defined as follows. Because we know that this prover must be complete, and therefore it must return the correct round polynomial for all of these different possible values of R. So here, we are just considering, even though the random challenges can be any elements from the field, we only really need to consider all the binary challenges, all possible binary challenges. So in particular, if the challenges were 0, 0, 0, 0, then the round s plus 1 prover must be able to like return the correct round polynomial corresponding to those values of R. And that is true for all of these possible values of R. And because of that, it must be true that the round s plus 1 prover can compute all of these different possible sums. And these sums just like are the values that you get when you plug in these values of R into that expression over there. Okay. And how many sums are there? There are 2 to the little s plus 1 equals 2s many sums. And it is able to compute these 2s many sums from pi and m. However, we also know that pi, the size of pi, sorry, that's a typo. The size of pi is at most 2, as at most s. And therefore, there must be at least s many sums that are computed by directly reading from m. Right? Because there are sums, because of just the storage constraints, there are some sums for which the storage cannot help the prover at all, and it must resort to reading directly from the input. Okay, and this is point 3 that we will use in the next slide, which is that s many sums are computed by directly reading from m. And now each sum is of the form, it's like a sum of like the evaluations over the Boolean hypercube of these many elements. And all of these sums are disjoint subcubes. So you can think of them as like s many subcubes, each of size 2 to the n minus little s minus 1, which is 2 to the which is n over 2s many input field elements. And if the prover is able to actually correctly return all of the sums of these subcubes, and all of these elements in these subcubes are themselves like arbitrary field elements, then it would have to read all of these values in order to be able to correctly return the sums of these subcubes. It can't avoid it cannot get away with not reading even a single one of them. And therefore, the prover would need to read at least n over 2s times s equals n over 2 many input elements total. And that is, we have now achieved our new goal that we set before. And we can now similarly show a similar statement like we did for round s plus 1 for the remaining rounds, 2s plus 1, 3s plus 1, and so on and so forth, that you need to read at least omega n many input elements in all of these rounds, and that gives you the final lower bound. And that is all I have for the proof of the lower bound. And again, in summary, we get like these 3 new results: upper bounds, lower bounds, better results in the PIOP model. And this is all the stuff that we proved in our paper, which you can find on this link, and you can find the implementation on this link. So thank you. Yep.
Amazing. Thank you very much. One quick question. For one question, we have time.
Yes, I was just curious to know if you tried to prove some upper bounds on other models like the one we saw this morning where there are multiple heads, that can jump around, or even in the random access model.
We were only considered with the single head streaming access model. For the multiple head model, I think that is like an interesting problem. And
yeah, because there's a mismatch in model, right? In the lower bounds, you chose the sort of the best model to prove the lower bound.
But like the thing is that the lower bounds are in a stronger model. So it's not that, so you can't actually, even if you like relax the model like a little bit, even if you made the model like random access, in that regime, at least if you made a random access, then you would not be able to get a better algorithm. But the multiple heads thing, I think maybe you can get away, if you have like a non-constant number of heads, maybe you can come up with like an interesting parameterization.
Yeah, for the upper bound, yeah, that's what I was thinking. Okay.
Amazing, thank you. Let's thank the speaker again. So next, we'll see some improvements for sum check proving, and I will give the mic to Suyash.
Okay, thanks, Oana. I'm Suyash, and I'll be talking about some of the engineering optimizations that we did to sum check specifically to Jolt, but it also applies more generally. I think Anubhav already covered this point that sum checks appearing everywhere, be it arithmetization, lookup arguments, folding schemes, ZKVMs. Everything's kind of boiling down to like one or multiple instances of sum check. And obviously this list is non-exhaustive. There's a lot of other papers or ideas that use sum check as the main primitive. Okay. So I'll just give a brief primer of why working on optimizations to sum check was becoming important. So I've put up this benchmarking example that we had in Jolt. So this is before the optimizations. So let's say you were doing this SHA-256 hashing of, let's say, either 1,000 or 2,000 hashes. Respectively, both of them cost around 3.6 million cycles, and the 2,000 hashes costs 7.2 million cycles. What we see is as the size of the number of cycles increase, the sum check contribution starts increasing. So sum check for 7.2 million cycles becomes like a 46% part of your end-to-end proving. So in 100 seconds, it's almost 47, 48 seconds that is consumed only by sum check. So we really thought improving sum check is really necessary for us to be able to get end-to-end improvement in Jolt prover. Jolt invokes a lot of sum check instances. for doing everything, it boils down to doing some check. But I'll specifically talk about two things that are worth focusing on, two sum check instances. The Spartan R1CS and something called as shout read address virtualization. I'll not explain how we get these equations, but these are just sum check instances that we need to prove to, in the first case, prove that the R1CS expression is correct, and the second, to prove that this read address virtualization was done correctly. So all of these polynomials that you see here are multilinear polynomials. And the goal of this is to run sum check instance over these expressions. The reason I choose these two as examples is the first one is a degree 3 sum check, while the second one is a much higher degree sum check. It could be like 5, 9, 17. It's a configurable parameter in Jolt, which will then decide the degree. So the right one is high degree sum check, the left one is low degree sum check. So it's a big spectrum that we were trying to target to come up with optimizations. For L equal to 23, which is the 7.6 million cycles that we saw, we were able to get like an 11x speed up for the low degree sum check and a relatively less impressive 1.7x improvement in the high degree sum check. After implementing all of our optimizations in Jolt Prover, we saw that only from the techniques from this paper, we got like a 25% end-to-end improvement. So the sum check that was 50 seconds or somewhere around 50 seconds in the previous slide is now about 23, 24 seconds. Okay. So I think Anubhav already talked about a basic primer on sum check. So I'll not go into a lot of details, but basically in sum check, what we try to do is we prove that the sum of a product of multilinear polynomials is equal to some C. The message or the round polynomial that the prover sends in every round looks something like this, where the first J-1 terms here are the round challenges. Sorry, this is in round J. The prover sends this univariate polynomial. So the red values, R1 to Rj-1, are the challenges from the previous J-1 rounds. And then we sum over the remaining L minus J. Actually, it should have been L minus J-1 variables, Boolean variables. The interesting thing to note here was that in Jolt, most of the witness values, so most of these evaluations of the multilinear polynomials are either 64-bit or even less. The sizes of the witness is generally small, like a lot of the witnesses are even Boolean. But the challenges need to be from the entire field. So the challenges are 254-bit because Jolt uses BN254. And as soon as we go to the second round, these challenges start blowing up the instance sizes because now everything becomes 254-bit numbers. And so the main insight of all of this work is, can we somehow exploit this smallness of the witnesses so as to avoid the challenges sort of poisoning everything into these large field elements. So that's the theme of the techniques that I'll discuss. Let's go to the first technique. First couple of techniques are pretty straightforward, and they not just apply to sum check, but could more generally be useful. So for the first technique, we're calling it small value multiplication. Consider that you have, let's say, two field elements. By BB multiplication, I'm saying big multiplication. So both of these boxes are two big field elements. And I'm showing 4 limbs for each of them in red, because BN254 uses 256-bit fields, use 464-bit limbs. And we know that multiplying 4 limbs by 4 limbs, we need n square multiplications. N is the number of limbs. And on top of that, we need this reductions as well, because we are working in a finite field. So we need total of 2n square plus n when doing this big multiplication. If we are doing small big multiplication, the small field element just has 1 limb. So you can immediately reduce the number of limb-wise multiplications to n, and you can use Barrett reduction to get total 2n plus 1. And interestingly, when you do just small multiplications, it's just one single limb multiplication that matters. You don't need to do any reduction, by the way, in the third case, because 64-bit number times 64-bit should always be in the field. So empirically, for BN254, a small multiplication is like 36 times, if we just plug in n equal to 4 in these expressions, a big multiplication is 36 times much slower than the small multiplication. And we also see this empirically. It's 29 empirically. And a small big multiplication, you can see, is almost more than twice faster than a big multiplication. So the point of all this is we must really, if our witnesses are 64-bit elements, we must really think about ways to avoid these BB multiplications as much as possible. Again, this is another simple trick called delayed reduction. We don't really need to, reduction is expensive, as we saw in the previous slide. So we don't really need to reduce until you really need to. So let's say you have to compute an expression of this form, summation Ci times Ai. Ci are small elements, Ai are big elements. So it's an SB multiplication. And then you need to sum over k of such products. What you can do is, instead of reducing in every multiplication, you just keep accumulating. So instead of restricting yourself to 4 limbs, we'll keep using 5 limbs. We'll perform the sum, and then we'll perform only one final reduction, Barrett reduction. Which means the SB multiplication that we saw on the previous slide costed like 2n plus 1 multiplications for one multiplication, and times k is the number of multiplications we are doing here. And this method, we just avoid all these reductions and we do one final delayed reduction. So it's almost like 2x improvement on the SB multiplications. So it's almost like a 4x multiplication if you consider it against the big multiplications. This is particularly important for low degree sum check instances, because you'll see this expression Ci times Ai sum over them mod B appearing in the sum check round computation. But this trick also applies more generally. Also, this same idea can also be applied to big multiplication, just that you'll have to reduce more frequently. Now I'll discuss like a couple of new tricks or new optimizations that we came up with. The first one is, we are calling it as round batching. So the interesting thing about sum check, and I glossed over this in a couple of slides before, is after every round, you need to fold the instance sizes by half. And for doing the folding, you use the latest challenge that is coming from the verifier. So for example, after the first round, once you get this R1 challenge, let's say P is your original multilinear polynomial, you bind the first variable to R1 by computing this linear combination. Now we know R1 is a big field element, like it's a full 254-bit field element. So what ends up happening is our original P had all small values. So let's say I'm just giving an example of, let's say, 16 values. As soon as we bind with R1, we go to all big values, because now multiplying with R and 1 minus R1 factor, everything blows up. And the idea is, can we avoid this? Can we avoid binding this after every round? And can we defer the binding till, let's say, V number of rounds? Turns out we can. And for that, we just need to build this single multilinear polynomial that should let us compute all the V round messages. It looks something like this. The expression is very similar to the sum check, original sum check instance. The only difference is we are keeping all these x1 to xv, the first v variables, intact. So the idea of this round matching is to treat Q very similar to what we do in regular sum checks. So Q will be used to generate all round messages for round 1 to V. And you can see the round polynomial, just like we bind the original polynomials, we can also do the similar kind of binding on the Q polynomial. So after each round, we bind the Q polynomial, but now the advantage is we are doing far fewer big multiplications, and I'll show how or how much. But the expression of binding is similar. After each round, we bind Q to the latest challenge that the verifier sends. This L Lagrange term, Lagrange of Rj, it's slightly different or slightly more complicated than this 1 minus R1 and R1 linear combination that we saw for actual binding or original binding, but it's similar. It's just a linear combination with some slightly more complex form of the challenges. So this Q polynomial that we had defined acts similarly to the so the size of Q also keeps reducing by half every round, after every round. So you define the first Q. From that you can compute the first round polynomial S1. Then you get R1. You bind the Q by R1 to get the next version of Q, and that process goes on. Okay, so let's come to the advantage of what this lets us do. If you look at the naive sum check, for the first V rounds, most of the cost of sum check is spent in the first few rounds, because every round the instance size gets reduced by half. So the bulk of your work you're doing in the first few rounds. So it would have costed us 2 to the power L, it's the total instance size, times D square big multiplications in the naive version. But with this round batching, what we do is we avoid these big multiplications and trade them for these small multiplications. So you see, for pre-computing this Q, we only use small multiplications, because if you remember the equation of Q, all of these values, all of these multiplications, pk, are small field elements, which means you can only use, okay, I'll just quickly wrap up. So the summary of this was that the BB multiplications no longer depend on the total instance size, and you trade them for the small multiplications. And concretely, you can see, theoretically, we can get like a 50x reduction or speed up just by doing small multiplications instead of BB multiplications. I'll not go over the couple of last techniques. They are in the slides. One of them is this product of multilinear polynomials, how we can do that efficiently. I'll just skip over this. And I'll just say a couple of words about the streaming version that Anubhav just presented. We also have a similar version where we perform this round batching. So here we can see for the first W1 rounds, we do the round batching, then the next W2 rounds, we do another round batching and so on, so as to limit the number of, the amount of data the prover has to store for each of these windows. And we actually improve on Anubhav's paper by, if you're doing like a high degree sum check, this D square term is the D square times whatever is this cost for the prover really blows up if D is high. We bring that down to D log D. That's a small improvement over the previous talk. And there's also a couple of other techniques I've included in the slide appendix. And thank you very much for attending.
Thank you very much. Are there some questions? Okay, I have a question. For trick number 3, when you are batching rounds, you choose value V and then you batch for V rounds. Is there some insight that you can give us how to optimize this V, or what are the trade-offs?
So if V is too large, we need to store this Q polynomial. So there's pre-computation cost of this Q polynomial as well as the storage cost. Typically, V equal to 3 or 4 is good enough. Even that gives us like a very decent speed up on the sum check, because most of your work you're doing in the first 3 or 4 rounds of sum check.
Thank you. Just one more question.
Related to the previous question, so with trick number 3, is it correct to say that you have, well, after you sort of delay the multiplication by the challenges, you probably have to do VBB multiplications, then V1 small bit by 1 BB, and then you have to add all of them, V minus 1. So I'm wondering if the VBB multiplications you have to do, every time doesn't like increase your cost too much. I guess that's related to how large you fix V, right?
If V is too large, then that cost can pile up for doing those delayed BB multiplications. So V equal to 3 or 4 gives this nice setup where you don't increase those BB costs. By the way, they are much less than what the naive version requires you to do BB multiplications, but V equal to 3 or 4 typically gives pretty good results.
Amazing. Thank you again. And thank you for all the improvements you have been making on SumCheck. Are we ready for the next speaker? So let's continue the nice stream of presentations on SumCheck. We have seen improvements on the prover. Let's go with some more improvements on the verifier. And yeah, let's see that.
I think I have this.
I have a mic.
Yes.
Alberto, please, the stage is yours.
Thank you. So hi, everyone. As she says, I'm going to continue talking about ways of using the SumCheck protocol, in particular to improve the efficiency of our recursion in the context of the Joule ZKVM. This is a joint work by Kwang, Sagar, Marcos, Justin, Andrew, and Michael. And this work, even though it applies to particularly the Jolt ZKVM, its techniques can be widely used in other contexts. So I think these are not my slides, or at least they are not updated. These are my slides, but they are not the ones that I recently sent. Yes, thank you. So we have two different ways of achieving recursion on ZKVMs. One is simple recursion, where we prove the proof that we get from a ZKVM inside a ZKVM. And the other one is wrapping. We compile the verifier of our proof into some arithmetic constraint systems like R1CS. And we want to make the verifier cheap in both, in the case of recursion, while minimizing the overhead of the prover. And as I said, this applies not only to Jolt. So one thing that the Jolt team has been doing for many years now is both applying the subject protocol to many different problems, but also to understand the structure of the computation to make it more efficient. And in this case, in modern snarks, we can see in many different talks this weekend that they are composed by a PIOP and a PCS. And also the verifier computes differently the PIOP and the PCS part of the snark. So in particularly the case of Jolt, we use the sum check. So the verifier for the PIOP does these sum check rounds, evaluation claims, and all these operations are over the scalar field of the prover. In this case, we call it FR. And in the case of Jolt, this turns out to be around 30 million cycles, which is about 2% of the total of the computation of the prover. On the other side, there is a part of the verifier that operates on the DORI, on the PCS of the snark, and those are group operations and pairing operations, and these are on a different field called the base field, and in particular is non-native to the Jolt prover. And because of this non-native arithmetic that we need to do for these operations, the verifier in the recursion for this part takes 98% of the total. To give you an estimation for a trace of 2 to the power of 20, this verifier in Jolt takes around 1.6 billion cycles. So, as I was saying, one thing that they do very well is understanding the structure. In this case, we have a verifier composed by two different sub-verifiers that don't share an intermediate state. So we can see the PIOP, or the verifier for the PIOP, producing opening claims, and the verifier for the PCS checking them. And each half can be verified independently. So the idea is as follows. We want to extend the initial proof with two sub-proofs, one proving the PIOP and one proving the PCS part of the snark. So in particular, this auxiliary proof, we call it PCS, certifies that the checks with this PCS are satisfied. So for that, we need a second curve to make it more efficient. And we can compute them in some sequentiality. So we do first the PIOP part and then the PCS. These techniques are different to folding. So we can say that we have some benefits, in particular that there is no IBC, folding accumulator, running instance, and so on, which make be more complex, arguably. And of course, we achieve that the verifier is of the PCS snark is native to the recursion layer. So just to mention curves that are used in Jolt, particularly, we use BN254 for the prover, and it has a cycle of curves with another curve called gramping. And we want these group operations to be native in the second snark we call by PCS. And one thing to note is that gramping is not pairing friendly. So that limits our options for which PCS we can use to prove this. In particular, Jolt uses Harax, which is a transparent, and it doesn't need pairings. It's not a pairing-friendly curve. And one thing to note is that the verifier is O to the square root of n. So in particular, that's 2 MSNs of size square root of n. And we are focused in this work particularly to minimize the committed data. And one technique that is widely used in this work is virtual polynomials. So we now are going to construct our PCS. And for that, all these checks that we were talking about, all these group operations and so on, they will become their own PIOPs. And this process will be constructing different PIOPs and then combining them together to some unique evaluation point at some point. So to understand first the operations that the Dory verifier does, we can identify 3 phases. That the first one, we get all this information from the prover, which are group elements, and then it does some operations in sigma rounds that it updates these accumulators, seed, E2, E1, E2, and so on. And then it does one final pairing check. And the PCS snark only proves the first 2, and we leave the multi-pairing as outside this proof to be checked directly by the verifier in our recursive layer. And because it's a fixed, constant number of operations, it doesn't add much to the total cost. In particular, I think it's around 9%. And this table gives an idea of where the cost of these operations land. So we see that all of them are linear to sigma, which is the number of rounds. And we can see that the most operations come from the target group of the pairing. And not only that, but also operations in the target group are more expensive. So we are going to focus on those operations. And just to note that the operations, or the PIOPs that derive from the operations on U1 and U2, just follow standard textbook techniques. They're also on the paper that is upcoming on this work. And we are not going to see them in any depth here. So there are 2 types of operations on the target group. There is multiplication and exponentiation. The target group is basically an extension field of degree 12. So we can represent any element of this target group as a polynomial of degree less than 12. And multiplication is equivalent to this equation with some quotient polynomial and our G, which is the irreducible polynomial of degree 12. And the way we do these things with SumCheck is we encode these coefficients as multilinear extensions. In particular, we use some 4-variate, we will see in a moment why 4, and we create our constraint C, so that we can run our SumCheck for this zero-check PIOP. In particular, the prover shows that this equation holds using the SumCheck protocol. Another interesting approach to how to prove exponentiation, we expand our exponent alpha of base 4, and thus we can create this chain of exponentiations. And the way we approach proving GT exponentiation in this work with this PIOP is by packing the entire chain into one single witness row with m plus 4 variables. M is basically the length of the chain, and 4 is the base that we choose. So in particular, for our curve in Jolt, m becomes 7. And the constraint is as follows. If you see the constraint is using the same technique as we saw earlier for multiplication. And you can see that basically row shift is equal to b times row, where b times row, yeah, where b is the log degree selector of the 4 elements powers of G. And one thing to note here is that row shift uses this shift sum check and is our first instantiation of how to use virtual polynomials to avoid committing to another extra polynomial. In this case, we don't commit to row shift because we already committing to row, and thus we don't need to commit to any other element in this equation. And as we did before, we also ran the PIOP, the zero check PIOP, with the same sum check protocol. And why base 4? Because we were saying that the verifier cost in hierarchy is dominated by how much data is committed, in particular is square root of n. It shows here that a shorted trace beats the benefits that we get from some low degree constraint. So we have covered GT, we haven't covered G1 and G2, but you can imagine it's similar with different operations. And now we have all these families, and we also want to check that the different elliptic curve PIOPs are consistent, meaning that the output of an operation will be the input of another operation. And that creates some sort of DAG, or directed acyclic graph, of sum-check instances. And one thing to note in this case is that the graph is quite small, so the verifier can compute it directly. And we avoid extra commitments as well. We avoid other techniques like the grand product polynomial or the permutation argument. So, as we were saying, we are now with these several sub-PIOPs, each one addressing one of these Dory operations. And this PIOP has its own witness multilinear polynomial fi with its own number of variables, which are all different. And after running all these sum checks, each of these polynomials will have a single evaluation claim. And we have C evaluation claims on these polynomials, each of which is of different size. So because we want to minimize data and because we know how the verifier for hierarchs works, we want to find an optimal way to address this problem. So the first two approaches are quite naive. The first one is committing each of these polynomials separately, and that will make the verifier pay for all these openings, each of which is a square root of the number of variables of that polynomial, and the cost of this particular case grows linear in C. Another naive approach is by padding. In this case, we achieve this one shape, one polynomial, one commitment, but the verifier is also linear in C, and in particular is quite more expensive than we would like. So this work shows a different approach called prefix packing, and we achieve all that we want, which is one commitment. We treat these FIs as virtual polynomials, and the work is less than 2 times the sum of this 2 to the power of ni. So just to dive a bit deeper into what this prefix packing does, we can treat this of each separate polynomials fi with a unique binary prefix, forming a prefix-free code. Prefix-free means that the unique binary element that we use to identify each of these polynomials is not a prefix of any other binary encoding of the other polynomials. And this is unique because of some inequality called Kraft's inequality. So we have our big polynomial f described as follows, and we can put some bound to this size of the polynomial. So once we have that polynomial, now we want to fold these claims into one via these subcube selectors. And the verifier in particular can compute the right-hand side of this equation on its own because it knows the selectors and it knows the claim, and the number of C in particular is small, is around a bit over 100. So for 19 rounds, this becomes a 21 variable polynomial, and it's quite small in terms of coefficients that we can compute efficiently. So just to finalize, we have some results showing the efficiency of this approach. So with the standard verifier, so the standard recursion, the verifier cycles are around 1.4 to 1.8 million for traces from 2 to the 16 to 2 to the 26. And we can see that we achieve almost, when I say we, the authors of this paper achieve almost an order of magnitude of improvement. So where the cycles go. So once we have done all this machinery, it turns out that the most work is left for the openings of the PCS that we use for this secondary auxiliary snark, which is the Hyrax openings. This slide shows that the recursion prover overhead is only 1.3 to 1.8 seconds, and the combined proof is a bit larger, but it's quite stable across all these trace sizes. And one technique that we haven't covered, so far we have been talking about the recursion using the Jolt ZKVM. This is now recursion using wrapping, meaning that we compile our verifier to R1CS, and we have different ways of proving that R1CS. And what's interesting is that the number of constraints for this extended verifier is less than 10 million, and is dominated by native field arithmetic. I think the only part that is not field arithmetic is the fixed number of pairings. So just to quickly mention the two approaches, we have option A, in which we wrap we prove our R1CS with Spartan and HyperKCG, and this is quite fast on a laptop for the prover. The proof size is a bit bigger than with Gross16, and the verifier is less than 10 milliseconds. The second option is Gross16. It takes a bit longer for the prover to run, around 7 to 10 seconds. The proof size, as we all know, is quite small, and it requires trusted setup. So the takeaways, again, as I was saying, we get out of benefits from understanding the structure of our computation, in this case of understanding the structure of the verifier in a recursive setting. And we extend our proof to a tuple of proofs. And we shift the checks for Dory to the prover. And we also don't need folding. If we want to do wrapping, and we want to maybe proof on chain and so on, we turn out to be, like, we come out with 10 million constraints from some R1CNs, and it can be proved via Gross16 or Spartan. If we want to prove this recursively with Jolt, then we drop the verification cycles from 1.5 billion to 200 million. And as I was saying, even though this presentation has been focused on Jolt, we can generalize these techniques with other settings as well. Thank you very much.
Thank you to our speaker. Let's start with some questions. We have time for a couple of questions. Okay, I will start the question session. I have two, actually. I'm wondering about two things. One related to efficiency and one related to security. Are all your efficiency improvements actually benchmarked from for a full implementation of JOLT, or is there something missing?
So the paper shows end-to-end implementation results for this. I haven't seen the code and I haven't run it myself.
Right. And since this is about verifier, we are always worried, or we should be worried, that we may introduce. So once we modify a possibly correct verifier, once we modify it with some improvements, we should be worried about security issues. Like, how certain are you that the new code you have introduced is efficient but also not buggy?
Anyway, yeah, in the paper they have proofs for each of these reductions.
And do you have like formal verification, or do you plan
Right.
ahead?
I'm sure the JOL team has a strong effort on formal verification. Probably Suyash also may know more about it, but yeah, at least they have proofs in terms of the source-equal lemma in all these operations for the PIOPs, each of these sub-PIOPs that we have for the different group operations. But I'm sure they also have efforts on formalization.
Okay, yeah, thank you.
Thank you.
And now, put it
Okay, we are ready for the final presentation of this session. And to finish off strong, we are going to see Thomas discuss compiler optimizations that have a good effect on ZKVM performance. So please, the stage is yours.
It's okay. Thank you. I'm Thomas from ETH Zurich, and I'll be presenting our paper evaluating compiler optimization impacts on ZKVM performance. This was done in collaboration with Stefanos from UCL, who's also here right now, with Todoris, and supervised by Changdong Su at ETH Zurich. So first of all, before I start, let me motivate the problem a bit more. So as we've probably seen yesterday and today, ZKVMs are becoming ever more important for verifiable and privacy-preserving computation. However, most ZKVMs out there, so for example, SB1, RISC0, or also JOLT that we've seen before, they're targeting regular ISAs, for example, RISC-V, and these were designed for traditional hardware and not proving systems. And motivated by this and also prior work, which has shown that compiler optimizations can actually hurt in these non-standard environments, we want to investigate how traditional compiler optimizations affect the performance of proving in a ZKVM. So how does that all fit together? So first of all, in a ZKVM, we would usually start writing a program in, let's say, Rust. So that's our guest program. And then we compile it to some binary in RISC-V via LVM. The executor then eventually replays that binary. The prover generates the cryptographic proof. And the verifier can then eventually check it. Now, in that step, we also have pre-compiles which might be used. But for our work, what's mainly important here is that LLVM is already in the toolchain and basically affects the entire downstream pipeline here, which also includes the performance of the prover and so on. So maybe first also a very small introduction into how LLVM fits into this and how it works. So LLVM is the compiler infrastructure behind Rust, Clang, and many others. And it's also used for all of the ZKVMs that we're testing here. So yeah, it has a front end that compiles to LLVM IR and then has a bunch of optimization passes. So for example, inlining, loop unrolling, and so on. And then has a backend which eventually compiles to assembly code. But both ZKVMs that we are targeting here and also Jolt, I think, they inherit LLVM as is and make very little changes to the optimization and compilation pipeline. So just to reiterate that, how that compares to traditional architectures for which compilers were designed. On ZKVMs, we don't have any caches, so we also have no cache misses that are penalized. We don't have any branch predictions. We don't have any out-of-order execution or ILP. Floating point is also something that has to be emulated, and unlike on regular CPUs, instruction cost is also almost uniform in all cases. So yeah, so let me also motivate why performance really matters here. So on a ZKVM, even just executing or like tracing a program is orders of magnitude more expensive than execution on a regular CPU. So yeah, improving then even further is orders of magnitude more expensive than that. So previous work on optimizations in ZKVM has mostly focused on improving the prover itself or doing things like pre-compiles or hardware acceleration. But what hasn't been studied so far is how compiler optimization and the generator code actually ends up affecting the performance of the entire system. So before we start, also a motivating example of how things can go wrong and actually do go wrong. So let's consider this function here, which does a basic division by 8. So on RISC-0, that regular unoptimized code would take 4 cycles to execute. But what the compiler would do usually is apply strength reduction to that. So it would then be compiled to a bunch of shifts and adds. But if we actually measure here how many cycles that takes, for example, on RISC-0 in this case, it actually doubles the number of cycles. And we also see that on x86, that optimization is actually very beneficial. So it makes the code about 3.5 times faster because division on regular machines is a fairly slow operation. But on RISC-0, we actually see a 40% degradation improving performance in that case. So now that I've motivated the problem and what we're trying to do, let me give a quick brief overview of our setup. So we have 3 research questions that we aim to answer. So first of all is how individual LLVM optimization affect the performance of ZKVM. Second, how different combinations of passes end up affecting performance, and whether there are any combinations that yield significant improvement or degradations. And third, also how exactly that compares to traditional architectures with the example of x86. Then, guided by these findings from these research questions, we want to identify untapped optimization potential and uncover where we can help improve ZKVM performance through compiler optimizations. So to study that, we collected a benchmark suite of 58 programs. That includes Polybench, which is a benchmark suite often used to test compilers. We added the MPB benchmark suite in Rust. Also some spec CPU benchmark, a bunch of cryptography workloads, and also other targeted programs, which also includes RSP from Succinct Labs, for example. Then we tested that across 71 optimization profiles, which includes 64 individual LLVM passes, as well as one completely unoptimized baseline. The unoptimized baseline here is without any Rust mid-level IR optimizations. And then we also have 6 standard optimization levels, which goes through O0, through O3, OS, and OZ. Also, one important thing to mention here, the difference between O0 and the unoptimized baseline is the Rust mirror optimizations. We tested that across 2 ZKVMs, RISC-0 and SP1, and the metrics that we are mainly targeting are execution time and proving time. Now let me start with the results from RQ1, so the impact of individual optimizations. So what we're seeing here is on the x-axis each LLVM pass, and on the y-axis the performance improvement or loss that we get when applying this LLVM pass. The blue line is like the average, and the shaded line is the standard deviation. So we see on both RISC-0 and SP1 we get actually fairly similar impacts, with the best on both being inlining, and the worst being loop invariant code motion, where we see a fairly significant degradation. These results we will later on then also analyze, so I'll be getting back to them in a few slides. So yeah, next for the second research question. Now that we have like all of the impacts of individual optimization, we want to see how the standard optimization levels in compilers end up affecting performance. And here we also see somewhat the natural pattern with O3 consistently achieving the highest gains, and OZ, except for O0, showing consistently the lowest gains. And now that we've seen that, and that O3 is also always doing the best on ZKVMs, the natural question is whether we can do better on that. And to do that, we use program auto-tuning using OpenTuner to optimize over pass sequences, optimization levels, inlining thresholds, link time optimization, and we're using cycle count as a fast proxy metric to guide our evolutionary search. Yeah, this is an example of one of the benchmark suites that we've tested with auto-tuning. And actually here we also see fairly positive results. So what we see here is the improvement that we get over standard O3 for each of these benchmark programs. And on average, we actually get a 17% improvement in proving performance by auto-tuning the compilation pipeline and selecting the ones that reduce cycle count the most. And we can also see that on some of these benchmarks, we even get a speed up that is more than 2x, so fairly significant. Yeah, so what we've seen in our 3 research questions, and the answer to this is that the performance gains that we get from these optimizations on ZKVMs is in general a lot smaller on than on x86, and for some passes the behavior flip entirely. So to study that and see why it happens, we consider 3 different cost components to analyze that behavior. So we consider cycle count, dynamic instruction count, which is fairly related because of the uniformity of instruction cost that we have. And then we also consider paging cycles on the RISC-0 in particular, because for some of the programs, this can actually be the dominating factor. Yeah. So if we actually analyze that across all of our benchmarks that we did, we actually see that these metrics are these cost components are very strongly correlated with the performance improving and execution that we get. So here are 3 passes. For each of them, we have these cost components and the corresponding performance gain in execution improving listed for each of the programs on the x-axis. And the key observation here, and from our statistical analysis, is that the dynamic instruction count that the program has is like the key driver of the performance that we eventually get. So based on that, we then derived 4 optimization principles and empirically validated them on programs in our benchmark suite. So the first one here would be to avoid excessive paging pressure and avoiding passes that greatly increase paging cycles. So one example here is where we had loop invariant code motion that caused more than 400% increase in paging cycles and then dramatically slowed down proving. The second is to inline selectively based on whether it actually ends up reducing instruction count. So inlining tends to be very helpful, as we've seen also in RQ1, but this is mainly only for as long as it can reduce dynamic instruction count. So it should be avoided if it then actually ends up causing stack spilling. Third, we should also unroll loops only when it actually helps reducing instructions. That also makes sense because on ZKVMs we don't have any ILP, so all of the benefit from loop unrolling that we could get is through the reduced overhead of branch checks, for example. And fourth, we should be a lot more conservative with branch elimination because we also don't have any misprediction penalties, and branches are in general very cheap on ZKVMs. The fourth point here, I can also illustrate with an example that we had on one program in our benchmark suite. So this is one of the polybench benchmarks where we have a function that computes the absolute value of some integer. And before the optimization is applied, we actually get a branched version. But what compilers will usually output is a branchless version. Which is a lot better on x86 because we don't get any branch mispredictions, and that actually results in 2.2 times faster execution on x86. But on ZKVMs, that's actually a very detrimental optimization to do just because of the fact that branches are really cheap in general. So based on these 4 optimization principles, we then made some very slight modifications to LLVM and tested them on both RISC-0 and SP1. So these are around 150 lines of code in total, so fairly small and targeted. And we actually see that, for example, here in execution on the ZKVM, we already significantly outperform standard 03 on a wide variety of benchmarks for both ZKVMs. So, for example, on one of the benchmarks program, we get up to 45% faster execution. On average, it's about 4.6% on RISC-0 and 1% on SP1. For proving also, we actually managed to improve performance on 27 out of 58 benchmarks program by more than 1% on SP1. And on the risk zero, we get 8 out of 51 programs where it's more than 1% improvement. There's one major regression on SP1 though, because one of our inlining changes there causes the number of shards to increase. Yeah, so based on this, what are the implications for ZKVM users and people actually working on ZKVMs? So for users, I think that means that O3 is already a very decent baseline. So we've seen that O3 of all the standard optimization levels already achieves the highest performance. Second would be that auto-tuning can pay off. So if you have a specific guest program and want to improve performance for that, you can actually get fairly significant performance improvement by auto-tuning that guest program. And as we've seen, large improvements over O3 are actually possible. And third point related to that also is that we can use cycle count as a very cheap proxy metric to improve the proving performance. For compiler and ZKVM engineers, on the other hand, our results imply that that LLVM heuristics are currently very blind to the ZKVM cost model, and yeah, that we can achieve these performance gains I've showed before using very small changes also exemplifies this. And what this also shows is that probably ZKVM specific backends will probably be needed instead of just reusing a standard LLVM backend targeted to a traditional hardware. Yeah, so this is a relatively unexplored area of ZKVM research, I would say. So there's a lot of potential for future research as well. So one of the things we could do is extend this study. So we did this on the risk zero and SP1 only. So this could be extended to Jolt and see whether, and so we can see whether our results generalize. We should also do more work on having ZKVM specific compiler backends that actually consider the ZKVM specific cost model. We could also do super optimization for ZKVMs, so where we find ZK optimal equivalents to some existing instruction sequences. Fourth, we can also or we should also do more work on having better cost metrics. So one example here is SP1, where we already have prover gas as a cost metric that's in many cases better than cycle count. And last, to basically get more information for the compiler to do these optimizations, we can also consider profile-guided optimization or something similar in the ZKVM context. Yeah, so that concludes my talk, and I'd be happy to take any questions.
Thank you very much. Any questions?
Thank you for the talk. In one of your earlier slides, you showed a comparison between SP1 and risk zero.
Yeah.
And it seemed like for one of the two, there were significantly fewer data points. I was curious what the origin of that was.
Yeah, I'm not sure if I can go back here, but you mean the slide from RQ1, right?
Yes, I think so.
Yeah, so I mean, like I said, we had like 71 optimization profiles. So on this slide, we only showed the profiles that had more than 1% impact on average compared to the unoptimized baseline. So what that means for SP1 is that a lot fewer optimization passes actually, yeah, did have like that of significant impact.
All right, thank you.
More questions?
Yeah, so
one other thing the compilers does is like register allocation, and I suppose in a ZKVM you're free to choose how many registers you have. Have you explored this to like find out whether it's better to have more registers or fewer?
No, that's not something we've explored, but yeah, I think that would be an interesting area to explore. I think my current guess would probably be that it would make sense to have more registers, but yeah, I also don't have any data on that.
Okay, thanks.
Do we have more questions? Okay, I have a more open question. You mentioned in the conclusion slides that you plan to extend the studies possibly to Jolt, but can you already, I don't know, have a prediction how this would work, or like what already your study how would work, or like what would not work, or?
You mean like the impacts of it, or?
Yes.
I mean, like what we've seen so far is that on SP1 and RISC-0, we actually get fairly similar results for each of the optimization passes. So my expectation would be that for Jolt, we also would see a similar picture, but yeah.
So you believe there is nothing inherently different with some check that would stop, or with, I don't know, one of the polynomial commitments or such that would, like, one of the, you know, arithmetizations, or that would stop to see the same improvements?
So I'm not too familiar with Jolt in particular, but yeah, I mean, I think it would definitely be worth it to check that, and I think our infrastructure could also be easily adapted to Jolt. I think the biggest hurdle there is just to actually run everything, because that takes quite a while, even with GPU acceleration. But yeah.
Okay, thank you. We'll wait for these results. Okay. So good work. Okay. Thank you very much. Let's thank the speaker again. Just to let you know, one small announcement. At 4 p.m. there is a group photo just outside of the hotel. So if we all can make it there on time. Thanks.
Hello. Okay. Our next speaker for this session is Ilian Gitter, and he will talk about confidential transfers for global payments.
All right. Hey, everyone. Thanks to ZKProof and the lovely sound people making me feel like I'm in a 90s boy band. It's fun. Okay, so I'm going to talk about confidential transfers on Solana, what we did, how we're enabling it, what we're actually going to be doing for hopefully some of the largest payment companies in the world. As we've seen on blockchains generally, right, we have everything visible on chain for the most part. The amazing work many of you guys are doing here is to make it so we can actually have private transactions, private information, and be able to do a lot with it. However, there are some problems on Solana that are maybe a little bit unique. We have fairly small transaction sizes, so about 1,000 bytes per transaction. And then on-chain in the accounts themselves, they're also a bit expensive, and you can have up to 10 megs on a particular account. And so when you have these two things, you end up with this constraint that you need to keep things cheap and small, and then also fast, because we do anywhere between 1,200 to 3,600 TPS live on mainnet. And so how do you deal with thousands of transactions per second while also trying to keep things private? So little intro for myself. I lead ecosystem engineering at Solana Foundation. I'm not a cryptographer. I've sort of just been trying to learn as fast as I can for this talk and this event, which has been amazing, and I have had a lot of fun learning and trying to catch up. So unfortunately, the creator of this protocol, Sam Kim, was unable to join, but he did teach me a lot about this whole process. So ZK on Solana at a quick glance here. We have a lot of primitives already available, and a lot of companies and individual projects building a lot of different ways of incorporating ZK into the stack. And there's a list of them down here. Feel free to look at them later. This talk, we're going to be talking about confidential transfers, which is a particular protocol on top of our standard token program, which exists on Solana. So unlike on EVM chains, which I imagine most of you are more familiar with, on Solana you have standard token program that anyone can use in order to issue and manage their token. So you don't write your own smart contract in order to issue a token on Solana. Instead, you just reuse this one token program, and then you can get everything out of the box that it has, including confidential transfers. And so a lot of companies that we talk to want to know, well, okay, great, I love the idea of a stablecoin. I love the idea of being able to send transactions around the world in a fraction of a second. The speed is amazing, the cost is amazing, but am I exposing my balance sheet? And the answer is basically yes, right? Everyone, if they're able to dox your addresses, you're able to also understand everything about the business flows of that company. And so a lot of companies are extremely interested in confidential transfers and what it can enable for them in their own B2B flows around the world. As far as full privacy, I do think that people do want it, but it's a spectrum, and many of the payment companies are happy with having the exposure of their addresses and the exposure of counterparties, but less so the exposure of the actual amounts. And so they're also used to a certain amount of privacy already in the payment network that they're used to, right? So on the right, we have what they're already used to, which is everything is basically hidden unless you're in this private little network or you're a corresponding bank or something. And so it's bad for what they want to be able to do. And that's what we're trying to solve here, right? So at a glance, what is this actually? What's this protocol? What's happening under the hood? What are people able to see? And how does this work? So we have individual token accounts that have encrypted balances using Twisted Elgamal in enabling FHE for these different transfers, and then different proofs that go along with it for when you're doing a transfer in order to actually make sure that you have integrity as well. So there's like the range proof, equality check, and validity. And then so on-chain, you're able to basically just see a 0 unless you have a decryptable key in order to actually see the amount for yourself. So senders and receivers can decrypt their own amount. And then there's also an optional auditor key, which an issuer can choose to configure for their token account to be able to actually decrypt any transfer that happens. And this one's extremely important. Issuers need to understand what's actually happening with their token. They need to expose this information to regulators. You have to actually be able to provide this information if you're going to bring this to scale. So selective disclosure plus these different setup under the hood here, right? So fairly straightforward, nothing too complicated or crazy here, but it does solve the immediate needs for all of these companies. Not, going to be it's not going to also work with Quantum yet, but we have some plans as to how to potentially upgrade. But that doesn't really seem to matter to people, to be honest. Not yet. They don't know. Okay, so step by step, how does it work? So like I said, we have a token which is using this token program, which everyone is using. You don't write your own smart contracts again, right? You're able to just reuse the standard. And so you configure your specific token with this confidential transfers extension enabled. Then you're able to set up your auditor public key to be able to decrypt the individual transfers, which are also encrypted to that public key. And then you set also a privacy level for that extension. So you can either have it, of course, disabled, opt-in, meaning anyone can create their own keys to be able to participate in this private transfers world, or whitelisted, where you basically have to have the issuer approve you and let you into that network. And then there's also a required setting here. So you could also just have it where every single transfer must be encrypted, right? That's also a setting here. On-chain, the auditor public key is available, as well as the encrypted balances and everything else. You can see that on-chain. The issuer policy in all of this is actually something that is fixed at the time of issuance, or at the time of creating the mint, but you can change these individual settings as you go forward. Okay, so then an individual, right now I am using this token. What do I do with it in order to actually get access to this? I create my own Elgamal key pair as well as an AES key in order to have an easily decryptable balance. I then publish this and create the token account on-chain for myself. So now I have an account that exists on-chain that is ready for a confidential balance. On-chain, we can see the Elgamal pub key, and then I can take my public balance and deposit it into my, my confidential balance, and be able to then move it from one public setting into the private setting. The reason it has to go this way is because you have to have the total supply, unless you're having the confidentiality required for the token, but most don't. You have to have the public supply visible, and then you go from that into the private balance. Okay, so then after it's deposited in here, I'm sort of skipping through a number of the individual things. Feel free to ask questions as I'm going through, of course, if you have questions on some of the lower level. Then you apply it, and this is because you need to be able to use that, use your private key in order to then apply it to your actual full balance. These are not UTXO based, this is account based, right? And so then you compress that down, or add it into your own encrypted balance, and then now it's ready and available for you to do any transfers with. So if we go to the transfer, you are submitting the 3 ciphertexts as well as the range proofs in order to actually do the transfer and put it on chain. Only the sender and receiver can decrypt and actually see the transfer, as well as the auditor, right? So, okay, so the primitives here, right? We have our grouped ciphertext 3 handles validity, which is making sure that everything is encrypted to the same scalar underneath. Then you have the quality of the ciphertext on either side, the sender and the receiver, and then we also have the range proof using bullet proofs under the hood in order to make sure that we're not cheating, right? And then after all of this is done, you can keep doing this transfer throughout the different folks on the confidential balance, and you can then transfer it back into the public side of things. And here on this side, we are using, oh, I didn't mention that there's the Pedersen commitment to open as well as the quality here. Great. This makes some sense. These are fairly basic things in the world today, but it is a way to keep things fast, cheap, and very simple. Okay, so some additional things that were added in here versus the original protocol include the AES key, which allows you to have just a very quick available balance that you can decrypt. The El-Gamal proof program is a separate Solana program that's available for anyone to use. As I mentioned on Solana, you don't usually write your own smart contracts, you reuse standards that exist on chain, which allows anyone to now access these different functionalities through the El-Gamal proof program and do their own protocols on top of it. This is all baked in for you now. The different primitives that we have here, we have the Pedersen commitments, which is actually hiding the amounts inside the ciphertext and proof witnesses. We have the twisted El-Gamal encryption, which is encrypting the balance and transfer amounts. The Sigma protocols in order to do the pub key, validity, zero ciphertext, and equality checks. The group multi-recipient validity, which I said is making sure that the encryptions all match. And then the bulletproof range proofs in order to actually do the proving the transactions are valid. And that's basically it. That's the whole setup here. We did have, this has been live for a couple of years, and then there was a bug that was discovered with, of course, Fiat Shamir, because that's usually what it is. And it has since gone through, I think, 4 more audits and a bunch of other things. But even that first version was audited 3 times. So it's difficult to catch, apparently. I don't know. But we have some of the amazing auditors in the room, so thank you for your help on fixing some of the problems. I don't think I need to go through this too much. It's basically what I had already gone through, but more of the proof workflow here. So on the left, we have what's done on the client side, the prover, right? We do have a WASM SDK, so you can do this in your browser as well, or in Rust in a backend if you would like. And then in the middle, we have the ZK El-Gamal proof program, which exists on chain, that is only verifying the individual proofs. It's not actually caring about the token, right? So this is a native primitive that exists. And then on the right, we have another token program, or we have another program on chain, which is the Token 2022 program, which is actually including this functionality into any token that wants to use this. So now that we have it, right, now that we actually have deployed this, how do we get people to use it? And that's actually probably the harder side to a degree, because there's a lot of companies that need to individually coordinate and adopt this as a standard. Not only do you have to have the issuers who want to use it, so the PayPals of the world, the SoFis, the Western Unions, right, all of these have said that they want to use this. You have to get them to then pressure the custodians or their issuer partners to actually implement this and figure out, how am I going to use this auditor key? What do I actually do with this? Do I want to have that power? Do I want to do like some threshold signature thing on it? Then there's the wallets. Then there's the exchanges. If they want to be in this, does this fit their compliance rules? I don't know. How do you do travel rule, right? Like all of these things that end up bubbling up from this desire here is a part that I think is going to take a little bit longer, but we do have some good conversations already going in order to get this to happen. Also, the transaction sizes, this will be solved in a couple months at this point, but right now, as I mentioned, the transactions are restricted to 1,024 bytes, and this whole like transfer construction is larger than that. And so right now it doesn't fit into one transaction, which means you have to actually stack 3 on top of each other. But in a few months here, or less than that even, we're going to be increasing the transaction size almost 4x, and so that's going to be fine across on Solana generally. And then there's also the composability, right? So how do we actually do more with this? How do we bring this into DeFi? How do we actually do trading on top of this? How do we make it so it's not just this isolated little like B2B trading world, or B2B like payments world? And this last one, it's an open question if we actually need it, because there are, like I mentioned at the beginning of the talk, a lot of different projects that are already live that are doing a lot more with other schemes. And so maybe this ends up just being the institutional solution just for payments, and I don't know, we'll see. And then, like I mentioned, the auditor key, right? So this particular piece is complicated to handle. You are able to rotate the auditor key. However, previous transfers are encrypted to the previous auditor key. So you're not able to keep that one forward, or you can't have forward secrecy on it. If that leaks, it leaks, right? So how do you actually manage this? Do you want to do, as I said, like maybe you do an MPC scheme with it and you're able to rotate the shares, right? So there's an open problem here as to what's actually going to become a standard and how people are going to be doing that. There's also questions from the regulators. What are they going to want to do with this? Is this fine? Does this fit into the Genius Act? Do they need to fit it in the Genius Act? Do we need the DFS to look at this, right? Like there's this whole other compliance and regulatory aspect that also needs to be weighed in here. And then what is the process for selective disclosure? Do you need approval from the sender or something, or the parties involved? Do you not need to? Do you need a warrant to do that? Do you not need to? Because everything has been private, or everything has been transparent on chain, there haven't really been the cases where like you actually need to answer that for individuals when this is baked into the protocol, right? We've had plenty of other experiences where privacy was the only option, and the selective disclosure has never really been tested in like the court of law. At least not on the on-chain side. Okay, so I have a little demo here. Hopefully it works. It's a live demo, so you never know. But so the setup that I have, this is running against DevNet. This is already re-enabled on DevNet. I've already configured a token. I've already set up my account to be opt-in. The sender and the receiver are already there. And I've already minted assets to this. So hopefully it loads. Here we go. So you can see everything right now because I have all of the private keys loaded up on my computer. So I'm decrypting these values live. And you can see the ciphertext, or a shortened version of it, which is the amount. And then you also can see the auditor view as well here, right? And then also the events that the auditor has seen in the past. So I tested this once before. So we have a previous transfer and a previous application of that balance to the end user. And then on the right, we have the public view. Basically, you just have the ciphertext. You don't really see much else. So if I push R, theoretically, we'll have 3 transactions created and sent on chain to Solana's DevNet. And there's the proofs that it's creating it on chain to be executed, and it's done. It worked, great. So we have $250,000 left in the sender. We have $250,000 pending for the recipient. And then the auditor can see that this transaction happened. And if I were to click this, it would go to our Explorer. I might as well. So you can see that the public Explorer has no idea what happened here. I pushed a fix to this yesterday, but I guess it hasn't rolled out to prod yet. But here it's integrating with, it's just to actually like decode what's happening here. But for now it just says unknown, but you can still see the program information here, the instruction data, and you know, the ciphertext that is included here, right? So we have all this, and we have some of the logs that happened. Okay. Cool, so now I can apply the balance. And there we go. now we have the 750,000 in the recipient as well here. So this is the scheme that we have on Solana. I think that it works quite well, and we will find out if it ends up getting used, but we definitely have folks interested. It's really a UX thing that we have to figure out from here on out. How do we actually derive the keys? How do we want to have a standard there? Do we let people just pick whatever they want? We have some suggestions that we've been sending around to folks. So on top of this, we're expecting Treasury rebalance, B2B settlement, any of the larger payment flows to be using this. As I mentioned, Western Union is interested, PayPal is interested, a bunch of these companies have this baked into their token and ready to go. But on top of this, we can also do a lot more interesting things beyond just payments. We can have some other things around private trading or sealed bid auctions. Or I heard that there's actually a university that is considering using this to do encrypted governance and votes and be able to actually do their own voting system. And you can even do it in a scheme where professors can have more of a say than the individuals with more tokens than what an individual has. So this exists for anyone in the room if you guys wanted to try it out. It's not that complicated, and AI is actually pretty good at using this as well and building things on top. So things that I would love to see are, some of these things that I had mentioned around the private trading. How do we combine this with shielded pools or anything else? What other primitives do we need on Solana? We've had, I think, 6 talks about some check, so maybe we should do something there because it's fun. And how do we also combine this with other things to keep up with Solana's speed? So maybe we need TEs instead of FHE completely on everything, right? There's a lot of teams thinking about this, but how do we make sure that we're able to keep things fast and still try to have privacy as much as possible? Okay, that's the entire talk. I have no idea where I am on time, but if you guys have any questions, please shout them out.
Okay, any questions?
Do you feel like adding a backdoor to your protocol was an unnecessary concession to the American regulatory state?
By backdoor, do you mean selective disclosure?
The auditor keys that can disclose the values of all of the transfers.
So it is optional, right? You can easily create a token. You can wrap a token in your own program, in your own token that doesn't have that. Go ahead. We're not forcing it on anyone, but Solana is very practical and pragmatic in the sense that if you want this to scale, you're gonna need selective disclosure.
There was a similar design decision that we faced in Zcash when Kedit proposed kind of an auditing feature that I considered to be a backdoor. And that was also optional per token. It was associated with ZSAs, which haven't activated yet on Zcash. But I argued successfully that that was the thin end of the wedge and that we should not include features like that. So just, as a counterpoint to what you said.
Sure. Yeah, it's an open argument, and that's why we have multiple chains doing multiple things, right? So we're able to hopefully push everyone forward, and as I said, take USDC and create your own fully private, non-audible version. Go ahead.
All right, more questions? If not, let's thank Ilan again. All right, our next speaker. Is it okay?
Correct? Oh, okay, okay.
All right, so let's welcome Weiji Wang from Yale University. He will talk about dynamic snarks.
Okay, hello everyone. So my name is Weiji Wang. Today I'm going to introduce dynamic ZK snarks. This is co-advised with co-authors Haralampers, Shravan, and Dimitris. So first of all, we all know ZK snarks. This is a tool which allows us to prove a statement without revealing anything about the witness with a short proof. With some motivated by some application I will mention in the end, our goal is to build a data structure for snarks. So briefly speaking, I want to build a snark plus some dynamic updates. This is because sometimes when we have a snark proof and we just modify the statement or the witness a little bit, but in this case we need to recompute the whole proof from scratch. So can we build some data structure so that we can dynamically update the proof? So briefly speaking, the definition of dynamic ZK snarks is the vanilla snark plus one update algorithm, which takes as input the old statement, the old witness, the new statement, the new witness, and the old proof. It outputs a new proof, pi prime, maybe with some auxiliary information, which is from the data structure to help compute the new proof. And one constraint of this update algorithm is the runtime of this algorithm should be sublinear to the statement size or witness size, because otherwise it could be trivial. We can just recompute the proof from scratch using the proof algorithm. To be honest, before our work, most existing snarks are not dynamic. So, for example, Planck, Spartan. So they are all built upon PIOP and polynomial commitments. So in their protocols, after the verifier picks some randomness, the prover needs to do some computation after based on the randomness. So if you just change the witness a little bit, then the prover will receive a new randomness from the verifier, and every computation after that will be discarded and recomputed. So in this case, randomness often leads to linear recomputation. And also in some situations like Growth 16 and some other protocols, there are some polynomial division occurred. And in this case, for example, for Growth 16, you need to compute a quotient polynomial. And if you change the witness a little bit, then the quotient polynomial also need to be recomputed in almost a linear time. So these reasons could lead to linear recomputation for existing snarks. So in this work, we present Dynaverse and Dynalog, which are the first dynamic ZK snarks, and they are all in the universal settings. And you see there's an update algorithm, and for Planck, the update is unavailable because it needs analog and recomputation. And for both Dynaverse and Dynalog, the update algorithm is sublinear to the statement size. And I want to mention that for Dynalog, although the update algorithm looks good, but we need the QASDBP, which is the same assumption required for GIPA. I also want to mention that there are two follow-up works after our work. One of them is for dynamic Growth 16 protocol, which also will appear at Eurocrypt this year. And another work is for designated verifier dynamic snarks, which remove the GIPA here, but the requirement is the verification is only designated. So it's like a balance and some trade-offs between them. So to introduce our construction, let's look at the NP relation circuit satisfiability problem. So basically, this is just a small variant of the Planckish arithmetization. So we are looking at the circuit satisfiability problem. So for this NP relation, the public statement is some public wires of the circuit. And we just, to make things easier, we just assume that gate number 1 to number n is addition gates, and gate number n plus 1 to 2n are multiplication. And so there are 6n wires, 3 per gate. And so there are 2 constraints for this circuit is satisfied. The first one is every gate is correctly computed. So if it is an addition gate, the left input plus the right input should be equal to its output. If it is multiplication, then it is the multiplication relation. Also, since each gate has 3 wires and there are 6n wires, we need to show that each wire is correctly connected. And this is done using a permutation, which indicates that, so for example, sigma 1 is equal to 2, which means the first wire is connected to the second wire, and they should be equal. And this can be characterized with a permutation. And as long as each z of I is equal to z of sigma of I, then the wire constraint is satisfied. Okay, so we are building snarks, dynamic ZK snarks for this circuit satisfiability NP relation. So our basic idea is to decompose the permutation I mentioned in previous slide. So basically speaking, our goal is to prove z of I is equal to z of sigma of I for every index. And for permutation arguments we know so far, like what we did in Planck, there are many randomness incurred, and as I said before, if you just change 1 bit of the permutation, then everything should be recomputed. So what we do is try to decompose this permutation. So consider picking any vector z1 to zk, any arbitrary vector of the same length. Then it is equivalent to show that there exists some vector h1 to hk such that the subvector or the partial vector z of j at the location I is also satisfies this. So basically, for one direction, we can just pick arbitrary z and compute such h from this equation and show the existence. And for the other direction, we can just, since we know that there exists such h1 to hk, the sum over such k equations will get to the left hand side. So these two statements are equivalent. So the basic idea is we pick some proper decomposition of the witness vector z. Then we deal with z1 to zk separately for both gate constraint and the permutation constraint. So our main contribution is we build Dynamo, which is a sparse argument for the relaxed permutation relation. So the relaxed permutation relation is just what we need here. For any specific j, we can show this relation based on some fixed permutation. So basically, our contribution is as follows. We decompose the vector z as we want, and we use Dynamo, which is a sparse argument for the relaxed permutation relation for each z1 to zk. And then we find some other approaches to deal with the gate constraints. So that's how we build dynamic snarks. For Dynamo, I just want to mention that this is a sparse argument. So the sparsity here means the approval time of this small snark of this argument should be linear to the Hamming weight of the statement and witness side. So basically speaking, if we do some decomposition of z, then the sum of the Hamming weight of each z1 to zk should be equal to n. So for example, we have square root of n, k is equal to square root of n, and each of them has Hamming weight square root of n. Then if we just need to update one of them, then the update time or the computation time for one Dynamo proof should be linear to square root of n. Okay, so I will not go to the details of the construction of Dynamo, but this is just what we need as the basic building block. So to build dynamic snarks, so what I will present next is I will present two decomposition of the z vector such that we can make use of the decomposition to build dynamic snarks. The first decomposition is we are going to build a weakly dynamic snarks here. So a weakly dynamic snark means we fix the initial statement, and every update will be computed based on this initial statement. So for example, we have the initial statement z, and we call it as an anchor. And we can build an initial proof, which is similar to the Planck proof. We can use Dynamo for the whole vector z, and we can use some tricks similar to Planck to build the proof of gates, which can be computed in n log n time. Then, whenever there's an update, like we modify k arbitrary locations, z prime is considered as the difference vector, and the z star is the new witness, state and witness pair. So basically, z prime, which is z star, the new statement is considered as z plus z prime, because z prime is the difference values. So if we modify only k locations, so z prime should have Hamming weight k. Right? So, okay, and we specify the set of modified locations as S, and which has size k. Then, what we do here is, first, we compute a Dynamo proof for z prime for permutation relation, and it should be able to compute it in order of k time. And so now we need to consider what we need to prove right here. So we need to prove the gate constraint and for the while constraint. So now the Dynamo proof for z in the beginning plus the Dynamo proof for z prime is sufficient to show that the new statement z star satisfies the permutation relation. So what we left to do here is to show that all the modified locations still satisfy the gate constraint, like the plus, the addition, or multiplication. So what we left here is proof of gates for every location in the modified set, and show that as long as this gate, some value related to this gate is modified, then it still satisfies the gate constraint. Because the main point is, outside S, every gate is satisfied. We have already proved that in the initial proof. So for this part, we may need some commitment to commitment to the modified values and to compute some. No, it doesn't have to be. I just put it in this way to make the figure easier to. Okay, so basically for this part, we need some commitments and some quotient polynomials involved to do the computation. But the main point is compute this part of proof should also be like almost linear to k. Okay, so this is a weakly dynamic snark based on some fixed anchor z. So if we like keep so the point here is if we like modify like k more locations, then the proof should still be computed based on the original anchor, and the proof time is linear to all the number of modification locations. And everything here I listed here should be considered as a pi star, which is a proof for the new statement and the witness. But still is constant size. And this naturally gives us a sparse snark construction. So for sparse snark, so it's most of the whiles are zeros and some is non-zero. Some of the whiles are non-zeros. So basically, the anchor should be considered as an all-zero vector. And yeah, this gives us this is a direct application of this protocol. So to build Dynaverse, we use the weakly dynamic snark as I mentioned before. So whenever we have some modification based on the anchor, let's examine how many locations we have already modified. So if k is smaller than square root of n log n, then we just compute a pi star as I described before in order of k time, which is at most the square root of n log n. If k is larger than square root of n log n, then we set z star as the new anchor and recompute everything from scratch. So this recomputation requires n log n time. And now we can, for the following updates, the number of updated locations should start again from 0. So whenever we need to compute the pi star based on the anchor, the computation time should be at most order of n log square root of n time. And the amortized time to do the recomputation is also like similar to an order of square root of n, because we only do the recomputation every square root of n updates. And I want to mention that this recomputation can be de-amortized based on some standard tricks. Okay, so this is the first construction, Dynaverse with square root of n update time. The second construction is Dynalog. I will not go to details, but I just want to show some intuition how we achieve this. So this is built upon some standard waterfall technique, which is similar to the hierarchical ORAM. So basically speaking, we have log n levels of exponential size. And whenever there's an update, we log the update to the smallest available level. And yes, and each level we will have a dynamo proof. So for each level, there are some records of updates. So we can build a sparse vector based on the updates. So basically, this can be considered as a decomposition of log n vectors. So each level also has a proof of gates for the updated locations. And in this case, with some de-amortized tricks as well, then we can make the update time polylog. And to make this work, we need some GIPA to aggregate the proof. Okay. So now I'm going to introduce some application of for this protocol. Some of the applications are discovered recently, so it might not appear in our submitted paper, but so for example, for this application, it appears, as I said, in one of our follow-up works. So this is called dynamic proof of index. So sometimes we have a vector A, and it has two commitments, C and C prime. So C is like the Merkle root of the original vector, and the C prime is the Merkle root of its sorted version. So we need this like, so for sometimes we need a sorted version as an index so that we can do some binary search or some similar stuff in databases or so on. So to make sure we can make use of that sorted version, we need a circuit to show that the sorted version is correctly committed. And we can build a snark to show that. And the point of such circuit is whenever there's an element in A is changed, we want at most polylog of numbers, polylog number of whiles is changed in this circuit so that we can compute, we can use sublinear time to recompute the proof. So for example, let's consider the application in verifiable databases. The server wants to show that the server wants to do a binary search for a vector, which is a database. And the server by itself computes the index, which is a sorted version of the database. And the server computes the commitment, which is of both the original database and the sorted version, which is C and C prime. To show that the server conduct a valid search based on the sorted version C prime, it needs to show that the consistency between the original commitment and the sorted version. So to do that, the server can compute a snark proof to show the consistency between them. The problem is the database could be changed over time. So whenever the original vector is changed, the server needs to compute a new proof to show that it's consistent between the old digest and between the digest of the original vector and the digest of the index. So with this dynamic proof of index, as long as this circuit, circuit itself changes at most polylog number of whiles, and we have a dynamic snark to support sublinear time to recompute the proof, then we can update the proof of the consistency between two digests in sublinear time. So this is the first application I want to mention. The second one is for passwordless login. So for example, to access a blockchain account, we can use OIDC like Google to help us log in. And Google basically signs some JWT token, which binds the ephemeral public key from the user and the blockchain address from the app. So the app itself may need to compute a snark proof to show that I know a token signed by Google which binds EPK and the address. So for multiple logins, the EPK could be changed over time somehow. Then in this case, we can just update the proof. We don't need to recompute everything. And the DApp can just use the update algorithm to generate the new snark proof to finish the login procedure. And from an ongoing preliminary experiment, we find that if we just change the ephemeral key, public key, then around like 25% of the wires is changed. So we hope based on some dynamic snark protocol, then we can build some previous works by just compute everything from scratch. The last application is for bounded step IVC. So basically, we try to build an IVC protocol without snark recursion. So the main point of this circuit is each iteration just involves some some wires changed in this circuit, and we can just update the proof of circuit to generate the proof for the new iteration. I will not go to the detail of this circuit, but if you are interested, you can go to our paper to find more details. That's all. Thank you.
All right. Any question for Weiji?
So let's say I'm an adversary who doesn't know all of the witness. I only know the parts of the witness that can be updated. Can I replay a previous proof and just update those parts and not need to know the whole witness?
Yeah, unfortunately not. So in current...
Well, I don't view that as unfortunate, because I would view that as an attack.
So basically, we will put the whole original witness in the auxiliary information as part of the data structure so that we can compute. But we discovered that for some specific circuits, like we will only update the wires once or some. So for some special case and some special circuits, it could be achieved if you don't know some older witness.
I'm not sure you understood the question. I wasn't asking whether it was, I wasn't viewing it as a feature that you might not need to know the witness. I was viewing it as a potential attack.
It's a requirement for our construction for now, but we haven't considered to view it as a feature or not.
Okay, I'll have to read the paper in more detail.
Have you considered that a case where maybe updates have a special structure?
Yes.
So maybe you want to say, I don't know, this subcircuit is updated.
Yes, we believe if the update has a specific structure, then we can definitely build better dynamic snarks. For example, we have considered the case that updates can only lie in a fixed set of locations, or the updates can only so each wire can only be updated once, or some specific structure like that. And although we don't put such cases in our paper, but we believe we can have much better protocols if the updates have a specific structure.
All right. No more time for questions. Let's thank Weiji again.
No? Okay. Yeah? All right. So what do I do now? Do I connect to what? Ah.
Yes, this is the key.
Okay. Yeah, okay. So this is a joint work with Matteo Campanelli and Dario Fiore. And okay, so in general in this talk, I will talk about provable security for certain types of cryptographic primitives, like a certain design paradigm, and specifically about when you compose primitives that are secure in the AGM, when you compose them with snarks, how do you prove security for those? And one key takeaway would be that this technique would allow you to unlock new instantiations for unbounded depth IVCs that can be built from a larger class of snarks and folding schemes that was not possible before. So by unbounded depth, I mean that this incremental computation can go on for like arbitrary polynomial number of steps. So this is what these are the type of protocols I'll be talking about. So composite protocols where there's like this inner primitive, primitive X, and then you put a snark on top of it to get the composite primitive Y. And the reason you might want to do this is that X has some properties and you want something extra, so then you put a snark on top to get those, because it's a very general purpose primitive. And it is used in, like, this type of design is really used in many places. So for example, you can use it to compress proofs or batch proofs where you have several snarks in the first layer that give you this vector of big pi. And then you don't want to send all of them out, so you compress them using another snark on top, which just proves that all of these input proofs verify. Another example is a folklore construction of aggregate signatures, where again you have several signatures, and instead of sending them all out, you put a snark on top to aggregate them. And something that has been more relevant these days is incrementally verifiable computation, which is essentially the same as example one, but it's like several steps of snarks composed on top of snarks. Okay, so how do we prove security of such primitives? Intuitively, like what we want to say is that if the snark is knowledge sound, which is the most basic security definition for snarks, and if this underlying primitive X is secure for whatever definition, for whatever relevant definition, then that should imply security for Y. And you would prove this by building a reduction, which would be like, okay, so for contradiction, let's assume there's an adversary against primitive Y who outputs this final output, little pi. And so because this is actually the output of the snark component, I could then build an adversary that has access, given access to the adversary Y, which then this would be an adversary against a snark. So therefore, by knowledge soundness, there should be an extractor, and I can extract the previous input, W. And now this is an output of primitive X. So I can build an adversary X. And because I assume that primitive X is secure, therefore this should not be possible. But an issue here is that when this underlying primitive X is secure in the algebraic group model, then this reduction wouldn't work. So before I explain what the issue is, I'll motivate a bit more why we consider the AGM. The reason is very simple. It's a very popular and common model to prove security of many cryptographic primitives, and especially for proving knowledge soundness for snarks, special types of snarks that are very efficient. For example, oh, wrong spelling, sorry. Grot 16, Planck, Lunar, etc. These are all constant size snarks, and they're proven in the AGM. Another reason is because AGM allows you to have a special property from extraction called straight line extraction. And this, I'll talk about it later, but this is very essential for getting unbounded depth IVCs. So using this property, for example, what we can get is like proof systems such as bulletproofs or folding accumulation schemes like NOVA, which already have knowledge soundness under a different model. For example, they have proofs and rewinding. With AGM, we can get straight line extraction for these protocols. And so then when we build IVCs on top of these, we would get unbounded depth IVCs, like provably secure unbounded depth IVCs from such primitives. And finally, AGM is like quite strong, so it can also be used for, it is used for proving advanced properties for other primitives, for signature schemes. For example, to show instantiations of blind signatures, multi-signatures, they can be proven in the AGM. Okay, so again, like just a brief, what AGM is. It's a model where we assume that the adversary gets some input group elements, G1 to Gn, and then it outputs Y, which is also a group element. Then we assume that it should give us this vector gamma 1 to gamma n, which explains how it computed Y given the initial group elements. This is the example from before, and I want to try and prove, like show you what the issue is when composing in the AGM. So here again, like layer 1, there are a bunch of Grot 16 proofs that are then compressed or aggregated using a layer 2 of another Grot 16 proof on top. So to prove it, well, first there's this adversary against the full scheme who gives you the final proof, little pi, and because it's algebraic, it also gives you group representations, gamma, this gamma vector. So we can apply, we assume that Grot 16 is secure against algebraic adversaries, so we can apply the extractor using both of these inputs to extract the previous input, which is this capital pi, the vector of all proofs. Now ideally we would define this as an adversary against the layer 1 of Grot 16, and then potentially invoke the extractor again to extract the initial inputs. However, here this adversary needs to be algebraic, and so the adversary that we define, it's not a valid one. And really that can't happen because when we apply this layer 2 extractor, it wouldn't know the group representations. So it can't give us that, and we can't build a valid reduction. So yeah, so then like putting it all together, the issue is when we try to do this reduction, and we want to reduce it to security of primitive X, we need to build an algebraic adversary, and we can't do that. Right, so the next thing I'll discuss is, well, how to solve this thing. Okay, so the idea is pretty simple. This is the slide from before, the layer 1 snark and the layer 2 snark. And here layer 2 snark is proving whatever it's proving that I'm signifying here with this circuit C. So the idea is, okay, so this is the actual output, pi 2. If I could just output even the intermediate proof, pi 1, directly, because it's an algebraic adversary, it would give me all the representations I wanted, so I can do the reduction. But of course, you don't want to output it explicitly. So then the idea would be to force the layer 2 prover to output this pi 1 in query it to the random oracle, so that we see it somewhere, but not explicitly as a part of the output. And then we would change the AGM model slightly. We would say that, okay, now the adversary also has access to the random oracle, And whenever it queries a random oracle with some group element, it is also telling me the representation. So in addition to an explicit output, explaining an explicit output, it also explains its oracle transcript. So now we can recover all the representation we wanted just by looking at the random oracle transcript. And this proof will never appear in the final output. Right, so concretely, this is the layer 2 snark prover, and we will just add this additional step where it needs to process the input Z1 and Pi1, extract the group elements from this, and query it to the random oracle. And then we change the circuit C slightly to C star, where it also proves that these responses are actually coming from the random oracle. And then to do the reduction, so this is Pi2 is the actual output of the composite protocol. And in addition to this, we get the transcript of the random oracle, which is this TR arrow. And because it's an algebraic adversary, we also get this gamma, which will have the group representations for both Pi2 and any group element that's present in TR arrow. So just applying the extractor, we will get the previous input. And now, because of how we define the modified circuit, we know that both of these inputs, Z1 and Pi1, can be found in the transcript, the random oracle transcript. And because of the new modified assumption, the group representations for this can be found in this gamma. And now you can invoke the extractor again and do your reduction. Okay, so now I want to talk why this is helpful for IVCs and getting unbounded depth IVCs. Just a little bit a background about IVCs. So they are special proof systems that allow you to prove proofs for streaming computation. So you have some function f that's applied a number of times to get your final output Zn. And IVCs would allow you to compute a proof for this in an incremental fashion. So first you'll compute the proof for just the first part and just propagate Pi1 to the next step till you get the last proof Pi(n). And the property the security property we want here is a version of knowledge soundness where the extractor is basically asked to extract every intermediate state. So all Z1 to Zn-1 and all the witnesses W1 to Wn. And this is different from Snark's extractor, which only extracts one thing at a time. Right, so a very common practical way of building IVCs is through recursive composition of Snarks. So you have step I. What we do is we define a recursive circuit, which consists of two components. The first component just proves that this function f for step I has been computed correctly. And the second component basically checks this snark proof pi I minus 1. So this circuit at step I basically says that, okay, this current step is done correctly, and everything till step I minus 1 was done correctly. In general, you don't need to use an argument system, a full argument system to do this, this construction. What you can use are slightly weaker primitives called accumulation schemes or folding schemes. And they're nicer because they're very lightweight. So your IVC construction is better. And right, so the prover gets these previous step outputs and the local witness WI. It will compute the function for step I. And now it has all the inputs to invoke the argument or snark prover on this recursive circuit and get the proof for this step. The IVC verifier is very simple. It just checks the last proof that comes out. And because at every step we guarantee that all the steps before this have been done correctly, it's enough to check the last proof. Okay, so right, just to mention, so now if this argument system that we're using to build the IVC, if it was secure with AGM, it would have the same problem that I just talked about before. So we can fix it by changing the prover by, again, adding this component, making it query the group element explicitly, and then changing the recursive circuit to prove the correctness of this query. And the important thing here is that now, because the extraction can just work by looking at the previous extractor's output, like the important thing here is that the extractor never needs to call the prover, the adversarial prover again. It's invoked once, and you get Z0, Zn, pi n, and now you just keep extracting from that. You never call the adversary again. And this is important because it gives you the following bound. It tells you that the soundness of the IVC scheme will be upper bounded by n times the soundness of the underlying snark. This means that well, n here is the number of times you repeat this computation, so the depth of the computation. So this means that n can be like arbitrary polynomial in the security parameter. And to put it in the context, usually if we want to prove the security of IVC, what happens is that it blows up exponentially in the depth and the security, the soundness error of the underlying snark, which means that most of the time it's only secure for constant depth. But what we want in practice is that we can keep using it for arbitrary depth. And just to point out here, there has been a previous work that tries to circumvent this limitation of exponential blowup, but it is only applicable for proof systems that are derived from interactive oracle proofs, and they don't really work for these AGM-based snarks. So here, what we will get is that we can now apply, like, get IVCs from these other types of proof systems. What is this? Oh yeah, I didn't. One thing that I didn't like really mention so far is like we're proving this random oracle inside the circuit, and so how do we do that? And again, the whole thing is that we want provable security. So this is an important question to answer. Here we use something called as relativized arguments or snarks. These are special types of snarks that are able to prove statements about oracles. And we know that we can't have relativized snarks for random oracles. So what you need is a certain, like a variant of random oracle that is very, like it's similar, but it has more structure. So it allows you to prove these statements. And some examples in the literature are these signed ROM and arithmetized ROM. And among these, the arithmetized ROM is like particularly interesting because it allows you, like it gives this generic lifting result where it says that if your underlying snark has some property in the ROM, when you replace the ROM with a ROM, it will also, this property will also be preserved. So essentially, if it was knowledge sound, it's still knowledge sound, and zero knowledge, then it's still zero knowledge. This is nice because you can just take any snark that works in the random oracle and then have a relativized version that works in AROM. You don't need to redo any sort of analysis to use this snark. Okay, so concretely, our theorem says you need to use relativized snarks for some oracle O, and we can use arithmetized ROM, for example. And if this snark is straight line extractable in the AGM and this oracle, then the IVC scheme that you build from this will be secure for arbitrary depth recursions. Okay, so before I wrap up this talk, I want to talk about other works that exist to basically resolve the same problem with AGM composition. So there's this work which defines a different AGM model called recursive. Well, they don't call it recursive AGM, they call it extended AGM, but I'm calling it recursive AGM. And it's a stronger version where it says that, so this is the usual AGM definition I have here. And in addition to this, it says that if any subset of this representation, group representation, so for example, gamma 1 and gamma 2, if they satisfy some predicate, this F lab, then that should also be explainable. So what this means is that if gamma 1, gamma L can be interpreted as a group element, if it's possible to encode it as a group element, then the adversary should give me representation for this too. And then, so it should give me gamma, and then if this itself can be, like if there's something in this latest gamma that can be encoded as a group element, then you should give me representation for that too. So it just keeps going on all the way to the last level of the recursion. As opposed to what we use in this work, which is like really the basic AGM with a random oracle attached on top of it. Apart from this, like this assumption, when you look at the definition, apart from it being new and also more complex, the issue is that this condition that, okay, if I look at this representation and if it can be interpreted as a group, then give me representation for that as well. This is quite protocol dependent. Like this function F lab or this predicate F lab really depends on the protocol that you're trying to analyze. This means that when you change your protocol that you're trying to, that you want to prove secure, the algebraic assumption would change. However, like in our case, it's like the assumption is very well defined. It's clear what is to be explained. It doesn't change with every protocol that you want to analyze. One interesting connection could be that what we do here, this technique is in a way, it is forcing this recursive behavior. Because it's forcing the prover to explain all these intermediate things. So it is a way of like having this recursive AGM concretely. A benefit of this recursive AGM assumption, and one reason why it was introduced, was because you don't need to change the protocol in any way. This is a much stronger assumption, and it allows you to prove security of schemes without changing them. So on the other hand, a downside of this technique that I just talked about is that you have to use relativized snarks, and they require you to modify the snark to adapt it to this other oracle. And so this construction that we will have here will be more heavyweight than if you were to use recursive AGM. So to summarize, I showed a very simple technique to prove security of composable, primitives that are formed by composing AGM secure primitives with snarks. And this has applications to unbounded depth IVCs and other primitives like aggregate signatures. And concretely, this gives us new instantiations for provably secure IVCs from proof systems like Groth16 and folding schemes like Nova. And finally, one open question that we can think about is that this, what we did in this paper was a very general, like we just assume a general circuit that can take care of group operations. However, what we would do is probably something like cycle of curves to implement IVCs. And it would be important to see concretely what happens when you use this. So for example, one thing that would happen is that you would have two parallel IVC chains, that has to be now linked together when you do this computation. Another question that I didn't really have time to discuss much, but so I'll just talk about in a high-level way. We have a result for showing, for proving a security of aggregate signatures, where signatures are secure in the AGM. And this requires special snarks called oracle snarks. And these are basically snarks that are secure in presence of arbitrary oracles or signing oracles. And in the paper, we show a very specific case. We show that KZG commitment scheme is secure in the presence of specific signing oracles, such as for BLS and Schnorr. So it would be interesting to see what generic properties you wouldn't want from signatures and commitment schemes to get like generic OSNARKs. Okay, yeah, that's it.
Any questions for Mahak?
So this construction, if I understand correctly, required changing the circuit to query a random oracle. Is that right? Does that run into concerns about soundness of fiat shamir when the circuit references the oracle?
I think so. First, like you can have an idealized, like you do have a provable security in some model, which is like this AROM, arithmetized ROM and such. And it's true, when you heuristically instantiate this with an actual hash function, there might be similar problems as we see in like fiat shamir attacks. Matteo?
So no, we're not in the circuit. We're not proving that we're querying the random oracle, and it's actually not the random oracle. It's so what you do, you prove something else in the circuit. So you're basically folding and deferring something that eventually is going to be at the end something about a random oracle, and then at the end the verifier is going to be like, okay, let me query the random oracle at the end. So at the end of the the unfolding, yeah.
Maybe you should discuss this offline, but is it something that's much cheaper than the actual hash function?
I don't remember, but it isn't. So the question to do you incur into problems for fiat shamir? The answer is no. This is also from a previous technique by paper by Alessandro and others. And the other question I don't know, and we can take it offline. And maybe yeah.
Okay, I don't think we have time for more questions, so let's thank Mahak again.
Madonna, io proprio quel tizio, cazzo, veramente io voglio avere una macchinetta. Allora, let's go, schiva.